Hello there and welcome to Science for Sleep, where curiosity stretches out, settles in, and makes itself comfortable for the night. I'm glad you're here, settling your thoughts, just enough to let them drift along something gentle. Tonight, we're easing into a question that sits quietly behind everything you've ever seen, touched, or wondered about. Why does the universe have structure instead of dissolving into a featureless haze? Why do stars exist at all instead of fading into scattered particles? Why do galaxies swirl instead of dispersing into emptiness? Why does anything come together in a way that forms patterns we can recognize, rather than dissolving into chaos so complete we wouldn't be here to describe it? Before we dive into all the layers wrapped around that question, take a moment to notice where you are. Perhaps you're listening from somewhere familiar, maybe wrapped in evening stillness, or maybe somewhere bright and busy with life continuing in the background. Wherever that is, I'd love to know where you're listening from tonight, and whether you're winding down, taking a break, or simply keeping a quiet companion close as you rest. It's always comforting to imagine people scattered across their own places while sharing the same slow story together. If you find this kind of peaceful exploration helpful while you relax or settle in for the night, it would mean a great deal if you liked the video or subscribed. It helps this calm corner of science reach others who might need a moment to soften their thoughts too. Now that we've taken a breath, let's begin letting this big question open gradually, the way the night sky reveals itself one detail at a time as your eyes adjust. Because even though the universe might seem vast and intimidating, it begins to make sense in small steps when we follow the traces of how things came to be what they are. It's easy to assume that the universe is structured because that's what we see. We look up and recognize constellations, even if we know they're only patterns drawn by our eyes. We see the Milky Way stretched across the sky on a clear night, or images of swirling galaxies that look like someone arranged them with intention. We recognize planets orbiting stars and moons orbiting planets, forming neat arrangements that seem almost orderly compared to the chaotic noise we sometimes associate with nature. But if you strip all of that away and imagine everything starting from scratch, it's not obvious that the universe should work like this. It could have been a place where matter never clumped together, where nothing cooled down enough to form anything stable, where particles drifted without ever encountering each other long enough to build something more complex. So, the fact that the universe didn't collapse into chaos or expand into emptiness without forming any shape at all becomes a puzzle worth unraveling slowly. Take the earliest moments after the beginning of everything. For a long time, people imagined the early universe as an explosive event, flinging matter outward like debris from a violent collision. But that picture doesn't quite match what scientists now understand. The early universe wasn't a chaotic spray of random fragments. It was incredibly hot, incredibly dense, and surprisingly uniform. So uniform, in fact, that if you had been able to look at it, you would have struggled to find any differences from one point to another. Yet hidden within that smoothness were the tiniest irregularities. Not dramatic differences, just small variations. Slight changes in density that were hardly noticeable compared to the overwhelming sameness. Those tiny variations are where the story really begins, because structure needs something to work with. Without even the faintest imbalance for gravity to tug on, nothing would gather or settle or accumulate. Everything would spread evenly until no point was different from any other point. There would be no stars, no galaxies, no planets, and certainly no living beings trying to make sense of it all. So, the early universe wasn't chaotic at all. It was almost too smooth, except for these small differences that would eventually grow into the shapes we know. And that raises an interesting question. Why weren't those early conditions perfectly uniform? Why were there any differences at all? The best understanding scientists have now is that those earliest differences came from quantum fluctuations. These are minute changes that happen at incredibly small scales, so tiny you couldn't see them with any instrument we have now. But in the early universe, when everything was squeezed together and space itself was undergoing rapid expansion, these small fluctuations were stretched out to cosmic scales. They became the seeds that gravity would use to begin pulling matter into clumps. You might imagine those slight differences as tiny dimples or slight swelling points that appeared not because anyone designed them, but because the rules of physics allow small variations to exist. When the universe expanded, those variations grew along with it. Gravity, patient and persistent, began pulling material toward those slightly denser spots. It took time, and the early universe was so hot and energetic that matter couldn't settle easily. But as things expanded and cooled, those differences became more pronounced. Over time, those dense regions attracted more and more material, creating growing centers where future galaxies would form. Not organized yet, just beginning the long process of gathering enough matter for something recognizable to emerge. Though it may seem like structure requires careful planning or precision, in reality it began from something much simpler. Small variations and the steady influence of gravitational attraction working over immense stretches of time. Even the idea of gravity shaping the universe isn't as straightforward as it sounds. It's tempting to imagine gravity as a force pulling things together in a direct and purposeful way. But gravity is less like a rope pulling objects, and more like the natural tendency of matter to follow the pathways carved into the shape of space. When there's a little more matter in one place than another, it creates a dip that other matter naturally falls into. That process spreads outward, tugging more and more material along. Slowly, irregular clouds form and grow. They rotate, collapse, heat up from the pressure, and eventually produce the first stars. Those stars gather into larger groups until you get the earliest galaxies. What's interesting is that this process doesn't require perfect timing or specific instructions. It simply follows the basic interactions between matter, energy, and gravity. This doesn't mean the universe is deterministic in an everyday sense, where every event must unfold in a specific direction. It means that the rules guiding matter are consistent enough for structure to emerge when the initial conditions allow it. If those initial conditions had been different, maybe with no fluctuations or with fluctuations too extreme, things might have turned out differently. A universe with no variations would have been permanently smooth, while a universe with too many variations might have collapsed into dense clumps too rapidly, making long-term structure unlikely. The more we look at how things formed, the more it becomes clear that the universe ended up balanced in a delicate way. Not perfectly balanced, but in a range where structure can grow steadily without immediately falling apart. When stars formed, they produced heavier elements through their internal processes, then released those elements when they reached the end of their lives. Those materials became part of new stars, planets, and eventually environments where life could emerge. All of this depended on the early conditions allowing structure to begin, but structure alone was not enough. It also needed time, stability, and the ability for the universe to cool at just the right pace. As we consider why the universe didn't dissolve into chaos, it becomes clear that chaos itself has different meanings depending on where you look. On one scale, everything is moving, changing, colliding, expanding, and heating. On another scale, order appears naturally as matter distributes itself along the shapes gravity creates. The universe contains both motion and stability, both predictable patterns and elements of randomness. Yet despite all the motion, it doesn't collapse into disorder so extreme that nothing recognizable can emerge. Instead, structure and interaction find a way to persist. All these ideas may seem large and complex, but the deeper you move into them, the more they resemble familiar patterns we see around us. Things gather together because of small differences that grow over time. Stability forms when conditions allow it. Systems develop intricate shapes not because someone arranges them, but because natural rules guide how each part responds to its environment. The universe is not a strict machine nor a complete accident. It's something that grows patterns because it has a set of consistent rules and enough variation for those rules to create complexity. As these ideas settle into place, the question shifts gently from why the universe has structure to how that structure continues shaping everything we see. And there's still more to explore as we follow this unfolding story into deeper layers. where the rules beneath everything become clearer and the reasons for structure become more grounded in the way matter behaves. When we look closely at why the universe formed the way it did, it becomes difficult to avoid noticing that everything we see is guided by a set of rules operating quietly beneath the surface. These rules don't shout for attention or announce themselves with any kind of drama. They don't bend to preference or opinion. They don't adjust themselves depending on who is observing them. They simply persist, shaping the behavior of matter, energy, and space in ways that become visible only when we look at the results. Whether it's the way particles interact, the way stars form, or the way galaxies rotate, these underlying rules act as the steady framework that makes structure possible. Without them, everything would drift into nothing meaningful, and the universe would lose the patterns that make it recognizable. So, easing forward from where we left off, it's helpful to settle into the idea that structure didn't appear because the universe was lucky, or because matter organized itself by chance. It appeared because the rules that govern everything allow, encourage, and support the formation of patterns. You've likely heard people refer to the laws of physics as if they're commands written somewhere, but these rules aren't instructions handed down from a source. They're simply descriptions of how nature behaves. They help us understand why particles attract or repel each other, why energy flows in certain directions, and why matter responds to forces in specific ways. When we say the universe has rules, we mean that its components interact consistently enough that we can describe their behavior with equations or principles. These rules are quiet in the sense that you don't notice them directly. You only see their influence. You don't see the gravitational equation in the night sky, but you see stars and planets gathered because of it. You don't see the principles of quantum mechanics floating in the air, but you see the results in the structure of atoms. You don't observe the equations describing electromagnetism hovering around you, but you experience their effects every time light reaches your eyes, or every time any device around you functions at all. Consider gravity for a moment. People often imagine gravity as a force pulling objects together, but a more accurate understanding describes it as the way matter changes the shape of space. When space curves around something with mass, objects move along that curve naturally. This isn't a preference or a tendency. It's simply how motion works when space isn't perfectly flat. Gravity doesn't choose to pull things together. It doesn't weigh the pros and cons. It follows its own rule consistently. And because of that consistency, matter tends to gather instead of drifting evenly. These gatherings become clouds, then clusters, then stars, then galaxies. Without this rule, even if there were small differences in density in the early universe, they wouldn't have grown into anything structured. Everything would have thinned out uniformly as the universe expanded. But gravity alone doesn't explain the entire picture. The rules governing how particles interact are just as important. The early universe was not a gentle place. It was hot, dense, and filled with particles moving at high speeds. Yet even in that intense environment, particles behaved in consistent ways. They combined or repelled according to rules that never wavered. Protons and electrons formed hydrogen because the electromagnetic interaction between them made that combination stable. Neutrons played their part in forming slightly more complex combinations when conditions allowed. And as the universe cooled, these stable structures became the building blocks for the first atoms. If the electromagnetic force had been slightly weaker or stronger, stable atoms might never have formed, or they might have formed in such different ways that stars could not ignite. This brings up an important point. When people talk about the universe being fine-tuned, they sometimes imply intention. But a more grounded way of thinking about it is simply that the universe has a set of conditions that happen to permit long-term structure. If the rules were different, the results would change. That doesn't imply purpose or planning. It simply acknowledges that structure is possible because the rules fall within a range where stable interactions can exist. There are countless ways a universe could be arranged where nothing holds together. Particles might never bind. Energy might disperse too quickly. Space might expand in a way that never allows anything to gather. But the universe we live in has the opposite quality. It encourages self-organization because the rules nudge matter toward configurations that can last. Think about temperature and energy for a moment. The early universe was so hot that particles couldn't stay bound. If you heated anything enough, even here on Earth, it would break apart. Heat, after all, is just the motion of particles. The faster they move, the harder it is for them to stay attached. So, in those first moments, structure simply couldn't form. The rules allowed atoms to exist, but the temperature did not. As the universe expanded, it cooled, and the energy levels eventually fell into a range where stable structures became possible. Not because the universe aimed for that temperature or had a destination in mind, but because expansion naturally reduces energy density. The rules weren't trying to create structure. They simply allowed structure to appear once conditions crossed a certain threshold. The same is true for the nuclear processes that happened shortly after the universe began. There was a brief period when temperatures and densities were just right for creating light elements such as helium and lithium through nuclear fusion. That window didn't last long. Once the universe cooled past a certain point, those reactions stopped. But the rules guiding how nuclei stick together didn't disappear. They simply waited until conditions inside stars recreated the right environment for those reactions to continue billions of years later. Stars are essentially natural furnaces that take advantage of the same rules that operated earlier, compressing matter enough for nuclear fusion to begin again. These fusion processes generate heavier elements, which later become components of planets and living organisms. Structure grows layer by layer because the rules remain constant while conditions shift around them. One of the most important aspects of these quiet rules is that they are not optional. Matter doesn't get to decide whether it follows them. A star doesn't choose to form. It forms because the interactions between matter, temperature, and gravity guide it toward particular configurations. When gas gathers into a cloud and becomes dense enough, gravity forces it inward. As it compresses, it heats. When it reaches a specific threshold, nuclear reactions ignite. The star stabilizes because pressure from fusion balances gravitational collapse. If the rules were different, that balance might never form. Stars might collapse prematurely or never ignite at all. But because the rules are consistent, stars form throughout the universe, using the same process, regardless of where they appear. Even the structure within galaxies follows from these rules. When clouds of gas rotate, conservation of angular momentum forces them to flatten into disks. This is why galaxies, planetary systems, and even rings around planets share similar shapes. It isn't a cosmic preference for spirals or disks. It's the result of how rotation works in a system where collisions and friction gradually redistribute motion. The rules don't create identical outcomes everywhere, but they create familiar patterns because the same principles apply across the universe. Then there are the interactions that govern the smallest scales. Quantum mechanics often feels like a confusing set of behaviors that don't match everyday experience. But even here, the rules are consistent enough to support structure. Particles behave in predictable statistical patterns. Atoms form because electrons occupy stable energy levels. Molecules form because atoms share or exchange electrons in ways determined by quantum rules. These combinations create the chemistry that leads to complex materials. Without these quiet rules at the smallest scales, the universe would never progress beyond free-floating particles. There would be no chemistry, no planets, no life. What's interesting about these rules is that they don't guarantee a specific outcome. They don't force the universe to produce stars or galaxies or planets. They simply define how things behave when conditions are right. Structure emerges because the rules don't forbid it. They support it through consistent interactions. This means that even though the universe appears filled with complex arrangements, the underlying cause isn't complexity for its own sake. It's the simple, steady application of rules that allow complexity to build step by step. And these rules don't operate independently. They overlap and interact with each other. Gravity influences the large-scale distribution of matter. Quantum interactions shape the smallest building blocks. Energy and temperature influence which processes can occur at which times. The expansion of the universe sets the general conditions under which all other rules operate. Together, they create an environment where structure can grow without collapsing or drifting apart. You might think of it less as a strict hierarchy and more as a network of influences that support each other. There's something grounding in the idea that the universe doesn't rely on spontaneity to form structure. The rules themselves create stability. They ensure that if matter gathers in one place, certain things will reliably happen next. If temperatures reach a certain range, atoms behave in predictable ways. If gravity becomes strong enough, clouds collapse in familiar patterns. The universe becomes structured not because it's designed to be structured, but because the rules are reliable and the conditions allow those rules to operate fully. The next step in understanding why the universe built patterns instead of dissolving into complete disorder is to focus on the quiet influence of gravity and how it gradually shaped everything we see. Gravity isn't loud or forceful in the way we often imagine. It doesn't pull objects with obvious strength in every moment. Instead, it works steadily, patiently, persistently. It doesn't rush, it doesn't waver, and it doesn't need anything more than the presence of mass to begin shaping the universe. Because of that quality, gravity becomes the main reason matter gathers instead of drifting endlessly. It becomes the quiet sculptor behind clouds, stars, planets, and galaxies. If you want to understand why structure appears at all, gravity becomes an essential part of the picture. To get a sense of how gravity works at this scale, you can imagine the early universe not as a chaotic explosion, but as a hot, dense environment, filled with material that is almost perfectly spread out. There were no stars, planets, or galaxies in those first moments. There were no clusters, no swirling disks, and no familiar shapes. Everything was in a state so uniform that it could have remained that way forever. But gravity behaves differently depending on small differences in density. When one region has slightly more matter than another, even by the smallest fraction, gravity becomes just a little stronger there. That tiny difference starts a chain reaction. More matter gets pulled in, making that region slightly heavier. That increase in mass strengthens gravity further, pulling in even more material, and on it goes, step after step, over spans of time so long that the mind has to slow itself to take in the idea of how gradually this all unfolded. It's important to understand that gravity didn't begin by creating stars. It didn't produce anything recognizable for a very long time. Its earliest influence was subtle. It simply encouraged matter to drift toward regions that were already slightly denser. Those regions might have looked only marginally different from their surroundings. Perhaps they held a few extra particles in a small cluster. But gravity doesn't need large differences to start its work. It only needs consistency. Once material begins gathering, gravity keeps supporting that direction of movement. It doesn't stop. It doesn't reverse. It simply maintains the same steady influence over time. During these early stages, the universe was still extremely hot. Temperatures were so high that particles couldn't settle into stable forms easily. Even if gravity tried to bring them together, the intense energy bouncing through the early universe pushed them apart. The competition between gravity trying to gather matter and temperature, trying to disperse it, determined when structure could begin forming. For a long while, heat won. The environment was too energetic for matter to hold itself together, but as the universe expanded, everything cooled. The expansion didn't extinguish gravity. It simply lowered the temperature enough that gravity's influence eventually became strong enough compared to the energy of motion. This shift marks the beginning of matter gathering in earnest. One of the major steps in this process involved gas. The early universe was dominated by hydrogen and helium, gases produced during the first few minutes when conditions allowed nuclear reactions to create the simplest elements. These gases didn't form the structures we see now, at least not right away. Instead, they drifted through space, responding slowly to the slight gravitational differences around them. Over time, gas began to collect into large clouds. These clouds could stretch across huge regions of space, containing far more matter than anything we might be able to imagine from everyday life. But even at these sizes, they were still mostly empty. Gas in space is extremely thin compared to what we experience here. The clouds formed because gravity drew them together, not because they were solid objects. Inside these growing clouds, gravity started shaping smaller groupings of matter. These became the seeds of future stars. The clouds didn't collapse all at once. They didn't suddenly form bright points of light. Instead, they folded inward gradually, with some regions becoming denser than others, depending on their original variations in mass. Gravity kept drawing material toward those denser pockets. As more matter accumulated, the gravitational pull increased, and as that pull increased, more matter drifted inward. Slowly, the centers of these clouds grew dense enough to heat up from the pressure of all the material falling inward. That heating wasn't just a side effect, it played a crucial role. When enough material gathered and the temperature rose to a certain threshold, nuclear reactions began. These reactions marked the birth of the first stars. They produced light, heat, and energy that spread outward. But even this didn't happen quickly. It took millions of years for the first stars to ignite. That may seem like a long time, but in the context of cosmic history, it represents only a small fraction of the universe's timeline. Gravity didn't just create stars, it shaped them after they formed. A star is essentially a balance between gravity pulling inward and the pressure from nuclear reactions pushing outward. If gravity were stronger, stars might collapse before stabilizing. If pressure from nuclear reactions dominated, stars would expand too quickly and break apart. But because the rules guiding gravity are consistent, stars find stable states where they can shine for long stretches of time. That stability becomes essential for structure to continue forming. Without stable stars, there would be no long-term formation of heavier elements, no planets forming around stars, and no environments where life could emerge. Gravity also guided the formation of larger structures. Stars didn't form in isolation. They appeared in groups within the same clouds where they were born. Over time, these groups grew into clusters. Clusters formed within even larger structures known as proto-galaxies. These proto-galaxies weren't smooth, symmetrical objects at first. They were uneven, filled with interactions between clouds, stars, and gas. Gravity kept pulling everything together, smoothing out the overall distribution while allowing smaller structures to remain intact. As these proto-galaxies gathered more mass, gravity became strong enough to bring them into stable shapes. The rotation of these early galaxies determined their final form. When a cloud rotates, gravity pulls everything inward, while the conservation of angular momentum forces the material to flatten into a disk. This is why many galaxies take on a spiral shape. The rotation isn't a stylistic choice, it's simply the result of gravity working in combination with the motion of the material inside. Even after galaxies formed, gravity continued to shape them. Stars orbit the center because gravity keeps them bound. If gravity weren't strong enough, stars would drift away into empty space. If it were too strong, stars might collapse inward too quickly. But again, gravity works consistently enough that galaxies remain stable for billions of years. This stability gives the universe the chance to develop more complexity. Inside galaxies, gas can gather into new clouds. Those clouds can form new stars. Those stars can form planets. And every one of these steps depends on gravity maintaining its influence at all scales. What's interesting is that gravity's role isn't limited to gathering matter. It also determines how matter moves once it gathers. Stars orbit because gravity creates a central attraction. Planets orbit stars for the same reason. Moons orbit planets. The shapes of these orbits aren't random. They reflect the balance between momentum and gravitational pull. If momentum is too high, an object escapes. If it's too low, the object crashes inward. When those values are just right, stable orbits form. These orbits last for long periods, giving planets consistent conditions. Stability doesn't require perfection, it just requires a balance supported by gravity. Even planetary systems begin with the same process that shaped galaxies. Gas and dust gather into a disk around a new star. Gravity encourages small particles within the disk to collide and stick together. Over time, these particles form larger bodies, which continue to grow through further collisions. These interactions eventually produce planets, moons, and smaller objects like asteroids. The shapes they take depend on the distribution of material and the way gravity continues pulling everything inward. Nothing in these processes behaves erratically. Everything follows the same set of principles, allowing complex systems to emerge over time. Gravity's influence goes beyond what we can see. Even dark matter, which doesn't interact with light, responds to gravity. Dark matter contributes to the overall gravitational pull within galaxies, helping explain why galaxies rotate faster than visible matter alone would predict. Without dark matter providing this additional gravitational influence, many galaxies would not hold together. They would spin apart or fail to form stable structures in the first place. Gravity doesn't distinguish between types of matter. It affects dark matter, ordinary matter, and everything else with mass in the same consistent way. This consistency is what allows structure to persist instead of dissolving. If gravity changed strength or direction unpredictably, clouds wouldn't form stable regions. Stars wouldn't ignite in balanced states. Galaxies wouldn't maintain their shapes. Planets wouldn't stay in orbit. Everything would be unstable, and the universe would resemble a constantly shifting environment with no lasting features. But because gravity behaves the same way everywhere and at all times, it allows predictable patterns to develop from simple beginnings. Even the distribution of galaxies across the universe reflects gravity's influence. Galaxies gather into clusters, clusters gather into superclusters, and these form large-scale structures like filaments and voids. These shapes aren't random. They follow the paths carved by gravitational attraction acting on initial variations. Over billions of years, these interactions shape the cosmic web. This web isn't a deliberate formation. It's simply the result of gravity pulling matter along the most efficient path available, based on the initial layout of mass. What becomes clear is that gravity doesn't create order intentionally. It provides a consistent influence that allows matter to organize itself when given enough time. The universe didn't need planning or instruction to form structures. It only needed rules that operate dependably and initial variations that gravity could amplify. With these ingredients, structure became not only possible but inevitable. When people think about randomness, they often picture unsystematic movement, unpredictable behavior, or noise without structure. It's a word that usually suggests a lack of order, an absence of pattern, or a situation where nothing reliable can form. Yet when we look at the universe closely, randomness doesn't produce the kind of chaos most people imagine. Instead, it becomes a starting point, a foundation that supports structure rather than preventing it. Random processes appear throughout nature, not as disruptions but as contributors to the patterns we see. The universe didn't suppress randomness in order to form structure. It used randomness as a source of variation that allowed gravity and other interactions to create stable shapes across enormous scales. When we examine how structure emerged, randomness becomes an essential ingredient. To understand how randomness supports structure, it helps to think back to the early universe. Everything began in an environment that was extremely hot, incredibly dense, and nearly uniform. That uniformity is important. If the early universe had been perfectly smooth, with no differences anywhere, gravity would have had nothing to work with. If every region contained exactly the same amount of matter, gravity would have acted identically in all directions, leading to no growth of clumps or regions that could evolve into galaxies. The universe would have remained flat and evenly distributed. There would be no stars, no planets, and no observers to wonder why everything stayed so still. But the early universe wasn't perfectly smooth. It contained tiny random variations in density. These variations came from quantum fluctuations and other processes occurring during the first fractions of a second. They weren't organized. They had no direction. They simply reflected the natural behavior of particles at extremely small scales. These initial variations didn't create immediate structure. They were simply differences, tiny fluctuations that were neither planned nor prevented. Some spots had slightly more matter, others had slightly less. But these differences were enough for gravity to begin its slow work. Over time, gravity amplified the variations. Regions with slightly more mass attracted more matter, while regions with slightly less mass lost material to surrounding areas. This amplification didn't require coordination or precision. It only required that randomness provided something for gravity to act on. Without those small, random fluctuations, the universe would not have developed any of the shapes we now see. The idea that randomness can lead to structure may feel counterintuitive, but it appears in many natural systems. When particles move randomly, their collective behavior can produce stable patterns. Consider gas in a container. Each particle moves unpredictably, colliding with others, changing direction constantly. But when you step back and look at the overall behavior, gases follow consistent rules. Pressure, temperature and density emerge from these random movements. The randomness of individual particles doesn't prevent the system from behaving predictably. In fact, without that randomness, many of the stable properties of gases wouldn't exist at all. Random motion becomes a foundation for order at larger scales. A similar idea applies to the early universe. The distribution of matter didn't have to be carefully arranged to create structure. It simply needed variety. Randomness provided that variety. The early variations didn't have meaning or intention. They weren't patterns, they were starting points. But when gravity interacted with them, they began to develop into recognizable shapes. Structure doesn't require perfect alignment. It requires rules that operate consistently on the initial conditions. Randomness supplies the initial conditions that allow the rules to guide the formation of structure. The expansion of the universe played an important role in this process. When the universe expanded, it stretched the initial fluctuations across large distances. This didn't erase the fluctuations. It amplified them by spreading them out and giving them room to grow. The expansion didn't smooth everything into uniformity. Instead, it allowed the slight differences to become more pronounced. This set the stage for the earliest formations to begin. Without expansion, the universe would have remained too hot and too dense for structure to grow. Without randomness, the expansion wouldn't have produced the variety needed for gravity to create patterns. Even after the initial fluctuations formed the foundation for structure, randomness continued playing a part. When gas clouds started forming, the motions inside them weren't orderly. Particles moved in various directions. Collisions happened unpredictably. Waves travelled through the clouds in multiple patterns. These movements might look disorganized at first, but they produce outcomes that follow reliable principles. For example, when clouds of gas contract under gravity, random motion helps distribute energy and prevent immediate collapse. Without that motion, the cloud might fall inward too quickly, forming unstable objects that wouldn't survive long enough to become stars. Random movement slows the collapse, allowing the cloud to reach densities and temperatures that support the proper formation of stars. Whenever stars form, randomness appears again. The distribution of material within the collapsing cloud isn't perfectly even. Some regions end up containing more matter, which allows them to grow into larger stars. Other regions with less material become smaller stars or remain as leftover gas. These variations don't form because the process is planned. They arise because particles move independently, interacting through collisions and gravitational influences. This variation contributes to the diversity of stars. Without randomness influencing how matter gathers, stars would all be identical. Instead, the universe contains stars of many sizes and temperatures, Because random distributions played a part in shaping their initial growth. Once stars begin forming planets, randomness remains influential. Within the disk of material surrounding a newborn star, small dust grains collide. Some stick together, others bounce apart, and some break into smaller pieces. These collisions aren't coordinated, they're driven by motion that appears disordered. But over time, sticking events accumulate, creating larger bodies that grow into planetesimals. These planetesimals continue colliding in unpredictable ways, some merging to form larger planets, others scattering or breaking apart. If the collisions were too orderly, planets might form in patterns that don't match what we see. But because randomness influences these interactions, planetary systems develop a wide range of configurations. This is why some systems have many large planets, others have mostly small ones, and some contain planets in unusual orbits. Randomness doesn't prevent structure from forming, it enriches the process. It allows systems to develop complexity. Without variation, everything would follow identical paths. With randomness, systems can diverge, adapt, and build structures that reflect a blend of reliable rules and unpredictable influences. This combination produces outcomes that make the universe more diverse and dynamic. Even on the scale of galaxies, randomness continues to play a part. When galaxies form, they grow through interactions with other galaxies. These interactions involve gravitational influences that depend on the relative positions, velocities, and distributions of matter in each system. Because these factors vary, galaxy collisions and mergers produce a wide range of results. Some galaxies merge to form smooth elliptical shapes. Others interact in ways that produce long tidal tails, rings, or distorted structures. These outcomes don't follow a single pattern. They arise from the combination of consistent gravitational laws and the random arrangement of initial conditions. Despite all these random influences, the universe doesn't fall into disorder. The rules governing matter and energy keep structure stable. Galaxies remain bound by gravity. Stars maintain their balance through nuclear reactions. Planetary systems hold together through orbits that reflect the interplay between momentum and gravitational pull. Randomness shapes the details, but the underlying rules ensure stability. This balance between randomness and order becomes one of the key features of how the universe develops. An example of this balance can be seen in the distribution of galaxies across large scales. When scientists map the positions of galaxies, the pattern looks irregular up close. Galaxies are scattered in ways that might appear random. But when viewed from a larger perspective, the distribution follows a clear structure. Galaxies form clusters, clusters connect into filaments, and filaments surround large empty regions called voids. This arrangement reflects the initial randomness of density fluctuations combined with the consistent influence of gravity. The large-scale pattern is not random, yet it contains variation within its structure. It isn't designed, but it isn't chaotic either. It reflects the natural outcome of randomness interacting with rules. The same principle appears in many fields. In biology, random mutations contribute to diversity, while consistent processes of selection shape the development of species. In meteorology, random variations in temperature and pressure influence weather patterns, while physical laws determine how those variations move and interact. In chemistry, random thermal motion leads to collisions between molecules, while the rules of bonding determine the outcomes. The universe uses randomness not as a source of instability, but as a generator of possibilities. Those possibilities become structured when natural laws guide interactions towards stable results. The idea that randomness can produce structure becomes easier to understand when we look at how many interactions occur at once. A single, random event might not produce a clear outcome. But when billions of particles, galaxies, or interactions occur, patterns emerge from the collective behavior. Randomness doesn't mean isolation. It means variation among many elements. With enough elements, consistent rules can shape the variation into stable systems. That's how randomness becomes part of the process rather than an obstacle. It's also important to note that randomness operates within boundaries. The universe doesn't give randomness complete freedom. It limits what randomness can influence. For example, the rules of gravity set the direction of matter distribution. The rules of quantum mechanics set the probabilities for certain outcomes. The rules of thermodynamics determine how energy flows. Randomness fills the space within those rules, but doesn't break them. This is why randomness doesn't erase structure. It works alongside structure rather than against it. As we reflect on all of this, the idea of randomness becomes less about disorder and more about diversity. It becomes a mechanism that introduces variation, allowing gravity and other influences to shape the universe into the patterns we see. The universe didn't need perfect conditions. It needed conditions with enough variation for natural laws to turn differences into structure. Randomness made that possible. It continues to influence the formation of stars, galaxies, and planetary systems even now. When people look at the universe today, they often see a place filled with enormous complex structures. Galaxies stretch across space with billions of stars inside them. Clusters of galaxies form larger shapes. Filaments of matter connect vast regions, and the empty spaces between them reach astonishing distances. Everything seems arranged in a way that feels intentional at first glance, even though we know it isn't planned. But when we move backward in time and picture the universe as it was in its earlier stages, it becomes difficult to imagine how such detailed structures grew out of an environment that looked almost perfectly uniform. To make sense of how cosmic architecture appeared, we need to understand how extremely small fluctuations, barely noticeable in the beginning, grew steadily into the shapes we observe today. In the first moments after everything began, space was filled with energy and particles behaving in ways that were influenced by quantum mechanics. These particles didn't sit still. They didn't follow smooth paths or distribute themselves evenly. They fluctuated. They shifted in density. They created areas that contained slightly more matter and other areas that contained slightly less. These differences were not large. They were extremely slight, often far too subtle for any observer to notice if one could have existed then. But they were enough to begin the long process of shaping the universe. Quantum mechanics doesn't allow a perfectly smooth distribution of anything. Even in the quietest conditions, particles fluctuate because of their inherent properties. These fluctuations show up as changes in energy, density, and motion. During the earliest fraction of a second, the universe expanded at an extraordinary rate in a process known as inflation. This rapid expansion didn't erase the fluctuations, it stretched them out. Something that might have been unimaginably small became large enough to span entire regions of future cosmic space. These stretched fluctuations created small differences in density that were preserved as the universe cooled and continued expanding. These differences themselves didn't produce anything recognizable. They didn't produce stars or galaxies. They were simply areas where matter was slightly more concentrated than their surroundings. But because gravity responds to mass, it responded to these tiny differences. Regions that contained slightly more matter created slightly stronger gravitational attraction. That attraction pulled in more material from the surrounding space. This process didn't happen quickly. It unfolded over extremely long periods, with small accumulations building gradually into larger ones. As the universe continued to expand, the temperature dropped steadily. When temperatures fell low enough, the earliest atoms formed from protons and electrons combining. Once atoms formed, light could move more freely. This period left behind a faint imprint known today as the cosmic microwave background, a snapshot of the universe when it was still extremely young. That imprint still contains evidence of the tiny fluctuations that existed at that time. The small differences in temperature and density recorded in this background represent the seeds of all later structure. These seeds were incredibly small, but because the universe had vast amounts of time to evolve, they grew steadily. Gravity became the main driver of that growth. As matter accumulated in slightly denser regions, those regions pulled more and more material toward them. This process is known as gravitational instability. It means that once a region becomes even a little denser than its surroundings, gravity causes it to become progressively denser over time. The more mass it gathers, the stronger its gravitational pull becomes. This feedback loop turns small fluctuations into larger clusters. Over millions of years, these clusters became the earliest structures, long before they resembled galaxies or anything that would look familiar today. During these stages, the universe was still dominated by gas, mostly hydrogen and helium. These gases were spread across space, following the distribution of the density fluctuations. Where the fluctuations were slightly stronger, gas accumulated more quickly. Where the fluctuations were weaker, gas remained thin. This uneven distribution created a framework, almost like a scaffold, that guided the growth of the universe. But it was still far from creating stars. The gas needed to collapse into dense, compact regions before nuclear reactions could begin. The collapse of gas into dense regions wasn't straightforward. Gas doesn't fall inward like a solid object. It moves, flows, and heats up from pressure. When gas collapses under gravity, it compresses and becomes hotter. If the temperature becomes too high, the pressure can push material outward, slowing the collapse. The balance between gravity and pressure determined how quickly structures could form. Radiation from the early universe also played a role. Light interacting with matter added resistance to the collapse in some regions, delaying the formation of the earlier stars. But even with these limitations, gravity continued to strengthen the denser regions. Over time, the densest areas developed into what scientists call dark matter halos. Dark matter doesn't interact with light, but it still responds to gravity. It collapses into regions shaped by the initial fluctuations, forming invisible structures that provide an underlying framework. These dark matter halos acted like anchors, pulling in gas and helping it form the earliest recognizable objects. Gas falling into these halos began to form the first stars. These early stars were very different from the stars we see today. They were extremely massive, forming from pristine hydrogen and helium. Without heavier elements to cool the gas efficiently, the first stars grew to large sizes before igniting nuclear reactions. Once they ignited, they burned brightly and lived short lives compared to later generations of stars. But their formation marked a major transition. It meant the initial fluctuations had grown into structures capable of producing light for the first time. As these first stars lived and died, they influenced their surroundings. When they exhausted their nuclear fuel, many of them exploded, spreading heavier elements into the surrounding gas. These explosions stirred the gas, creating new variations and disturbances that helped shape later structures. The material they expelled became part of new stars, introducing elements like carbon, oxygen, and iron into the process. These heavier elements allowed clouds to cool more efficiently, promoting the formation of stars that were smaller and longer lived than the first generation. The growth of cosmic architecture didn't stop with the first stars. As time passed, gravity continued pulling matter into larger regions. Small structures merged into larger ones. Dark matter halos grew through repeated collisions and gradual accumulation. Gas settled into these halos, forming rotating disks that eventually developed into galaxies. These galaxies weren't identical. Their shapes and sizes depended on the initial fluctuations that influenced how matter gathered. Some halos formed large galaxies, while others formed smaller ones or groups that interacted frequently. Even after galaxies formed, the influence of the early fluctuations continued. The arrangement of galaxies across space still reflects the initial pattern imprinted in the early universe. The large-scale structure, often called the cosmic web, resembles a network of filaments, sheets, and clusters. These shapes are not smooth or symmetrical. They follow the distribution of the early fluctuations, which determined where matter concentrated and where it remained sparse. The regions between these structures, known as voids, correspond to areas where the initial fluctuations were weaker. The cosmic web is one of the clearest demonstrations of how tiny fluctuations grew into something enormous. It stretches across billions of light years, connecting galaxies through long filaments of dark matter and gas. The web wasn't planned. It emerged naturally from the interaction between initial variations and gravitational growth. The shapes we see now are simply the long-term results of those early patterns expanding and evolving over time. When we look more closely at individual galaxies, the influence of early fluctuations still appears. Some galaxies formed in dense regions where matter gathered quickly, allowing them to grow large. Others formed in areas where matter was more spread out, resulting in smaller or more irregular shapes. Interactions between galaxies also depend on these early conditions. A galaxy's neighbours, its environment, and its future path are influenced by the initial distribution of matter. These conditions aren't random anymore by the time we see them. They follow directly from the tiny variations that existed at the beginning. Even the formation of stars within galaxies reflects the same pattern. Regions with slightly higher density in gas clouds form stars more readily. Where fluctuations are stronger, clusters of stars emerge. Where they're weaker, gas remains diffuse. The architecture within galaxies mirrors the architecture of the universe as a whole, shaped by variations that began on the smallest scales. The key idea is that structure grows from small differences, not from overwhelming forces acting suddenly. The universe didn't form its architecture in an instant. It formed it through gradual accumulation, guided by rules that remained steady. The initial fluctuations didn't need to be large or orderly. They only needed to exist. Gravity amplified them naturally. The expansion of the universe stretched them into patterns. Over time, the combination of these influences built everything that followed. All of this shows that cosmic architecture didn't arise from randomness alone. It came from randomness interacting with consistent rules over long periods. The earliest fluctuations contained no patterns by themselves, but once gravity and expansion acted on them, they became the starting points for everything else. Structure didn't need a blueprint, it only needed variation combined with stability. The universe provided both. Before exploring the growth of the earlier structures, it helps to step back and look at what the universe actually was during its first long stretch of time. Instead of the vast, complex space we can observe today, it existed in a state that was far simpler, yet still rich with the conditions needed for everything that followed. The earlier stages weren't filled with stars or galaxies or anything resembling familiar shapes. They were defined by temperature, density, expansion, and the presence of matter and energy that behaved according to a set of rules that remained consistent as the universe changed. To understand how order emerged, we need to examine the environment where the first hints of that order began to appear. After the universe expanded from its initial state, everything was incredibly hot and dense. This wasn't a heat that can be compared to anything on Earth. Temperatures were so high that particles couldn't form stable bonds. Protons, electrons, and other fundamental particles moved with energies that prevented them from combining in any lasting way. Instead of atoms, there was a hot plasma in which light couldn't travel freely. Photons scattered constantly, bouncing off particles in every direction. The environment was not chaotic in the way we think of chaos. It wasn't disordered because particles misbehaved. It was simply too energetic for stable forms to exist. This stage lasted for hundreds of thousands of years. During this entire period, the universe expanded. Expansion did more than increase the size of space. It reduced the temperature steadily. As the temperature dropped, particles slowed down. Their motions became less aggressive. The plasma persisted for a long time, but it changed gradually. Light continued scattering, and matter remained unbound, but the overall conditions were shifting toward the possibility of forming stable structures. Even in this early plasma, the small fluctuations in density that existed from the beginning were still present. These tiny variations weren't erased by the scattering of particles. They remained as regions where matter was slightly more or slightly less concentrated. Gravity acted on these regions, even though the environment was dominated by radiation. but radiation exerted pressure that opposed the influence of gravity. When radiation pressure is strong, it pushes outward, preventing matter from collapsing easily. This balance between gravity and radiation set the stage for how the early universe behaved. Neither influence dominated entirely. Instead, they worked together to shape the environment. As the universe expanded, the balance shifted. Radiation lost energy faster than matter did. Radiation pressure weakened. Gravity didn't grow stronger, but its influence became more noticeable as radiation pressure declined. This slow shift didn't immediately create structure, but it made the conditions more favourable for structure to appear. The early universe reached a point where matter could begin forming more stable arrangements, but it still needed one more major change before that could happen. That change arrived during a period known as Recombination. Around 380,000 years after the beginning, temperatures dropped low enough for electrons to combine with protons and form neutral atoms for the first time. Once atoms formed, light no longer scattered constantly. Photons began travelling freely through space. This release of light created the cosmic microwave background, a faint glow that still fills the universe today. It's not a glow you can see with your eyes, but it can be detected with instruments. That glow carries a memory of what the universe was like at that time. The tiny variations in temperature recorded in it mirror the early density fluctuations that existed before atoms formed. With atoms now stable, the early universe transitioned from a plasma to a gas. This gas was mostly hydrogen and helium. Light could travel through it without scattering, and the environment became transparent. This transparency didn't create structures by itself, but it removed the barrier that had kept gravity from acting more effectively. Radiation pressure no longer pushed outward in the same way. Gravity became the dominant influence on large scales for the first time. Even though gravity was now able to shape matter more directly, the gas was still spread out across enormous distances. The early universe wasn't filled with clouds or clusters. It was mostly uniform, with slight differences remaining as the only indication of where structure might eventually develop. These slight differences were small, but gravity acted on them in a consistent way. Where the gas was slightly denser, gravity pulled more matter inward. Where the gas was less dense, gravity pulled matter away. Over extremely long periods, these effects grew in strength. But it wasn't a simple collapse. Gas doesn't fall inward neatly. It moves unevenly and heats up. When gas compresses, it resists further compression. Pressure builds. This interplay between gravity and gas pressure prevented immediate collapse into stars or clouds. Instead, the gas needed time to cool. Cooling allowed matter to lose energy and collapse more effectively. Without cooling, the gas would resist compression too strongly, and structure would form slowly or not at all. Cooling in the early universe occurred through the emission of radiation. Atoms can release energy when their electrons transition between energy levels. This process allowed the gas to shed heat gradually. The more energy the gas released, the easier it became for gravity to pull it together. This cooling process wasn't fast. It took millions of years. But during that time, the earlier structures began to take shape. Dark matter played a significant role in this stage. Dark matter doesn't interact with light or radiation. Because of that, it didn't experience pressure from photons the way ordinary matter did. Dark matter responded only to gravity. That gave it the ability to collapse more quickly than gas. Long before ordinary matter formed clouds, dark matter gathered into large diffuse structures known as halos. These halos weren't objects in the way stars or planets are. They were vast regions where dark matter accumulated because gravity acted on it efficiently. As dark matter gathered into halos, it created gravitational wells that ordinary matter fell into. Gas collected inside those wells, guided by the distribution of dark matter. These early halos became the backbone for later structure. Without them, gas wouldn't have gathered into the regions where stars would eventually form. The earliest order in the universe came from the distribution of dark matter, responding to the small fluctuations produced during the earliest moments. The gas that fell into these halos didn't collapse immediately. It moved in various directions, compressed in some regions and spread out in others. Turbulence arose, the density varied. These differences produced small structures within the halos. Some regions became dense enough to continue collapsing, others remained diffuse. Over time, the densest regions developed into the earliest clouds capable of forming stars. These early clouds were massive. They contained far more matter than anything familiar today. Their sizes reflected the scale of the dark matter halos that gathered around them. Within the clouds, cooling continued. Gas contracted further. Temperatures rose as compression increased. Eventually, the dense regions became hot enough for nuclear reactions to begin. The first stars ignited. These stars were extremely large because the conditions of the early universe favoured the formation of massive stars. They burned brightly and lived short lives, but they played a critical role in shaping the environment. The earliest stars produced radiation that influenced surrounding gas. They heated nearby regions, preventing immediate collapse. They created pressure that pushed gas outward. But they also produced heavier elements through nuclear fusion. When these stars reached the end of their lives, many of them exploded, spreading these elements throughout the surrounding gas. This added variety to the composition of matter, allowing later clouds to cool more efficiently. With more efficient cooling, star formation became more steady, and the universe entered a period where stars and galaxies emerged more easily. As the earliest stars appeared, the universe began transitioning from a place with very limited structure to one filled with growing patterns. The earliest galaxies formed when gas settled into the largest dark matter halos. These galaxies weren't identical. Their shapes and sizes depended on how matter had been distributed at the beginning. Some halos formed large galaxies, others formed smaller ones. Many small galaxies merged into larger structures. Gravity guided these interactions. Galaxies moved toward each other because the regions between them contained slightly less matter. The early universe wasn't crowded, but these gradual motions brought galaxies closer over time. Even the movement of galaxies reflected the earliest fluctuations. Regions that began with more matter became the centers of clusters. Areas with less matter became voids. The earliest distribution of matter set the foundation for the arrangement of everything that followed. All of this shows that the early universe wasn't a place of disorder. It was a place where temperature, density, radiation and gravity interacted in predictable ways. The order didn't appear suddenly. It developed slowly as conditions changed. The earliest stages created the backdrop for structure. Cooling allowed atoms to form. Transparency allowed gravity to dominate. Dark matter created early environments for gas to collect. Gas cooling and collapsing created the first stars. Stars created heavier elements. Heavier elements allowed more cooling. More cooling allowed more stars, and so on. The order we see today began as a series of transitions that unfolded over enormous periods. None of the early steps resembled the galaxies we observe now, but each step built on the last. Reaching the point where stars begin to form marks one of the most important transitions in the entire history of the universe. Nothing familiar to us could exist without them. They are responsible for nearly every element heavier than hydrogen and helium. They shape the environments around them through radiation and gravity, and they influence how matter continues organizing itself long after they form. The earlier stages of the universe set the foundation, but it is in the formation of stars that the universe first begins producing structures with internal processes, ongoing changes, and long-term stability. To understand how cosmic organization unfolds, it helps to look at how stars take shape, not as isolated events, but as outcomes of the conditions that the universe had been preparing since its earliest periods. The environment that allowed star formation to begin was shaped by cooling, expansion, and the gradual gathering of gas into regions where gravity grew strong enough to overcome pressure. These regions weren't uniform or simple. They varied in density, temperature, and composition. Some areas contained more gas than others. Some cooled more quickly. Some had been altered by the first massive stars that existed briefly before collapsing. All of these factors influenced how the next generation of stars formed. None of these early steps produced the well-defined star-forming clouds that appear in later eras, but they set up the underlying conditions so that gas could behave in ways that led naturally to the creation of new stars. Gas clouds that form stars are shaped by the interactions of gravity and internal motion. When gravity begins pulling gas inward, the gas rarely falls straight to the centre. It moves in various directions driven by temperature differences, collisions and turbulence. Gas clouds are not rigid structures. They shift, compress, and stretch as material flows through them. Within a large cloud, certain regions eventually become denser than others. These dense pockets form because of slight variations in the distribution of matter. Gravity amplifies these variations by drawing more gas toward them. Meanwhile, the rest of the cloud continues moving, colliding, and cooling. Cooling is an essential part of this process. When gas compresses, the temperature rises. A hotter gas exerts more pressure, resisting further collapse. If cooling didn't occur, the gas would never condense enough to ignite nuclear reactions. Cooling in these early clouds happened through the emission of radiation from atoms and molecules. In regions where the gas contained elements produced by earlier stars, cooling occurred more efficiently. These heavier elements allowed the gas to release heat at lower temperatures. As a result, regions enriched by earlier stars tended to form new stars more easily. The earliest large gas clouds eventually fragmented into smaller pieces. Each fragment had its own internal structure, density, and movement. Gravity continued acting on each fragment independently, drawing material inward. These fragments were the direct ancestors of individual stars or groups of stars. They weren't smooth spheres. Their shapes evolved constantly as streams of gas moved through them, but each fragment experienced increasing pressure at its centre as more matter accumulated. When the pressure and temperature rose to certain levels, nuclear fusion became possible. The onset of nuclear fusion transformed these dense fragments into stars. Fusion begins with hydrogen nuclei colliding and combining to form helium. This process releases energy that counteracts the inward pull of gravity. Once fusion begins, the star stabilizes. The balance between inward gravity and outward pressure defines the star's lifespan. If gravity was slightly stronger or weaker, the stability would change. But because the rules remain consistent, stars form stable configurations across a wide range of sizes. The size of a star depends on how much gas gathers during its formation. Large fragments with abundant gas can produce stars many times the mass of the Sun. These stars burn through their fuel quickly, becoming extremely bright but living relatively short lives. Smaller fragments produce stars that burn more slowly and steadily, lasting billions of years. This range of sizes means that star formation produces diversity across any region where gas collapses. Star formation also produces additional structure. The gas surrounding a forming star doesn't disappear immediately. Some of it falls onto the star, increasing its mass. Some remains in orbit, forming a rotating disk. This disk doesn't require special conditions. It forms naturally because gas moving toward a centre can't lose all of its angular momentum. A rotating disk is the simplest way for matter to organise around a central mass when collisions and friction redistribute motion. These disks become the environments where planets eventually form. Even though planets aren't forming yet at this stage, the arrangement of gas into a disk sets up the eventual architecture of planetary systems. Within star-forming regions, individual stars rarely form alone. The gas clouds that collapse into stars usually contain enough material to produce several stars. These groups of stars form clusters. Some clusters remain bound by gravity, staying together for long periods. Others gradually disperse as stars drift away from their original positions. The interactions between stars in these clusters can influence the disks surrounding them. Radiation from massive stars can heat nearby gas, altering how planets eventually form. Gravity between neighbouring stars can disturb their disks, sending gas and dust into new paths. These interactions contribute to the diversity of planetary systems. Star formation doesn't occur uniformly. Some regions within a cloud produce many stars. Others remain quiet. Temperature gradients, gas density differences, and radiation from nearby stars all influence which regions collapse and which remain stable. Over time, the cloud becomes a patchwork of star-forming areas, quiet regions, and turbulent zones where gas circulates without forming stars. This uneven development is another form of structure. It reflects the variations in initial conditions combined with the consistent influence of gravity and cooling. Massive stars formed during these periods play a significant role in shaping their environments. They produce strong radiation that heats surrounding gas, preventing it from collapsing easily. They generate stellar winds that push gas outward. These winds carve cavities and channels through the gas cloud. When massive stars reach the end of their lives, they often explode as supernovae. These explosions send shock waves through the surrounding gas, compressing some regions and dispersing others. Compression can trigger new rounds of star formation, while dispersal can halt star formation in certain areas. The effects of massive stars create additional layers of organization in the cloud. Supernova explosions also enrich the surrounding gas with heavier elements. These elements contribute to cooling in later generations of stars. Each new generation forms from gas that contains more elements produced by earlier stars. This enrichment doesn't create uniformity, it introduces variation. Some regions contain more enriched gas, others remain dominated by hydrogen and helium. The distribution of these elements influences how future stars form, how efficiently gas cools, and how planetary systems develop later. As star-forming regions evolve, gas is gradually consumed or dispersed. The cloud loses mass as stars form, and as winds and radiation push gas outward. Over time, the cloud may no longer contain enough material to form additional stars. The remaining stars drift away, leaving behind a region that once produced thousands of stars, but now contains only the remnants of the original cluster. These remnants include stars of many sizes, planets orbiting some of them, and debris moving through interstellar space. The process continues across the universe. Gas clouds collapse and form stars in many regions, each shaped by initial conditions and local influences. Star formation becomes a continuous cycle. Gas collapses into stars. Stars produce heavier elements. Stars release material back into space when they die. This material becomes part of new clouds. New clouds form new stars. The cycle creates ongoing organization in the universe, turning simple gas into complex arrangements that can support more advanced structures. The large-scale consequences of star formation extend far beyond individual stars. The distribution of stars within galaxies creates additional organization. Stars cluster along spiral arms in some galaxies. They form dense central bulges in others. Their combined gravity influences the rotation of the galaxy. As stars orbit within galaxies, their motion reflects the distribution of dark matter and gas shaped by earlier fluctuations. These behaviors reinforce the patterns that exist on large scales. Even the behavior of galaxies is shaped by the long history of star formation. Galaxies interact with one another, merge, and influence each other's gas content. When galaxies merge, their gas can compress rapidly, triggering new rounds of star formation. These interactions add another layer of complexity to cosmic organization. They aren't chaotic, they follow gravitational rules, but they depend on initial conditions, including how much gas each galaxy contains and how their orbits bring them together. In later stages, galaxies settle into long-term patterns. Star formation continues in some areas and slows in others. Gas becomes depleted in certain regions. The environments inside galaxies evolve as stars age, move, and interact. This ongoing evolution adds further structure to the universe. New stars form in the outskirts of galaxies or along specific regions where gas remains dense. Old stars migrate toward different orbits. Stellar populations change over time. Each galaxy develops its own history, shaped by early fluctuations, dark matter halos, mergers, and thousands of cycles of star formation. As we follow this story, the idea becomes increasingly clear that star formation is not just about bringing light into the universe. It is one of the fundamental processes that organizes matter into stable, long-lasting structures. It guides the distribution of elements. It influences the behavior of gas. It determines the environments where planets can form, and it sets the stage for everything that develops afterward. By the time the earlier stars had formed and begun shaping their surroundings, the universe was already moving toward the next level of organization. Stars gathered in groups, gas flowed along pathways shaped by dark matter, and gravity continued guiding matter into larger and more stable formations. These early steps eventually led to the creation of galaxies, enormous systems where stars, gas, dust, and dark matter exist together in long-term structures. Galaxies didn't appear suddenly, and they didn't form according to a simple pattern. Their development followed from the interactions among matter, motion, gravity, temperature, and the underlying distribution of density established much earlier in the universe's history. Understanding how they formed requires taking a patient look at how matter behaved on increasingly large scales. The earliest galaxies began developing within dark matter halos, which themselves formed because dark matter responded to the tiny fluctuations left over from the earliest moments of the universe. These halos weren't small. They stretched across large regions of space and contained the majority of mass in those areas. Ordinary matter collected inside these halos because gravity pulled it inward, following the shape created by the invisible dark matter. Without these halos, ordinary matter would have remained more evenly distributed. It wouldn't have had a deep gravitational wells to fall into, and the process of forming galaxies would have been far more difficult. Inside these halos, gas accumulated gradually. The gas cooled as the universe expanded, making it easier for gravity to compress it. But the process wasn't uniform. Gas moved in streams, merged with other gas clouds, and experienced heating from early stars. These combined influences created complicated flows inside the halos. Still, the general trend was that gas moved toward the center of each halo. Once enough gas gathered in one region, it began forming many stars, creating the earliest recognizable galaxies. These early galaxies were not large or organized at first. They were small compared to modern galaxies containing far fewer stars. They were irregular in shape because the gas inside them hadn't yet settled into stable structures. Their growth depended on how much matter they could accumulate, how effectively the gas cooled, and how the surrounding environment influenced their development. Some small galaxies merged with others early on, increasing their size. Others remained isolated for long periods, developing at slower rates. The process of merging played a major role in shaping galaxies. When two galaxies came close enough, gravity influenced them strongly. Their shapes distorted. Gas moved from one part of the system to another. Stars shifted orbits. These interactions didn't happen quickly. They took place over hundreds of millions of years. But the long-term result of repeated merging was that galaxies grew larger and more organized. Each merger contributed material, altered the distribution of stars, and helped create the conditions needed for more stable shapes to appear. As galaxies grew, rotation became a defining factor. When large amounts of gas fall into a gravitational well, the gas doesn't simply collapse directly inward. Small variations in motion become amplified as matter flows through the system. Conservation of angular momentum ensures that gas with even a slight amount of initial rotational motion will speed up as it moves inward. This rotation prevents complete collapse into a single point. Instead, the gas spreads out into a rotating disk. This disk becomes the foundation for one of the most familiar galaxy shapes, the spiral. A spiral galaxy is not a rigid object. It is a system of stars, gas, and dark matter that moves according to gravitational forces. The stars in the disk orbit around the center. Gas circulates between stars. The center contains a dense region that may include a supermassive black hole. The disk maintains its shape because the motion of the stars and gas balances the gravitational pull from the entire system. If the motions were too slow, material would fall inward. If they were too fast, the material would fly outward. But because the motions are within a stable range, a long-lived structure forms. One of the most striking features of spiral galaxies is their arms. These arms are not solid structures. They are patterns created by density waves moving through the disk. As the wave travels, it temporarily compresses gas, triggering star formation. This is why spiral arms contain many young bright stars. The arms trace regions where the density wave has passed recently, not physical structures that rotate with the rest of the galaxy. This behavior emerges naturally from the physics of rotating disks. It doesn't require an external force or central control. The movement of matter within the disk creates the conditions that sustain the spiral pattern. Spiral galaxies are only one type of galaxy. Other galaxies developed different shapes depending on their environments and histories. In regions where galaxy mergers occurred frequently, the shapes often became more spherical or elongated. These galaxies, known as elliptical galaxies, contain older stars and less gas. Without gas, they don't form many new stars. Their stars orbit in random directions rather than organized rotations. Their shapes reflect a long history of interactions that disrupted the orderly motion found in spirals. Still, other galaxies remained small and irregular. These irregular galaxies didn't gather enough material to form stable disks. They didn't experience enough mergers to become elliptical. Instead, they remained scattered collections of stars and gas, influenced by nearby massive galaxies or interactions with passing systems. Their shapes are diverse, reflecting local conditions rather than clear patterns. Regardless of their shape, all galaxies share certain fundamental traits. They contain dark matter that forms the backbone of their gravitational structure. They contain stars that produce energy, generate heavier elements, and influence surrounding gas. They contain gas that moves, cools, and forms new stars, and they evolve over time as they interact with their surroundings. None of these traits appear by chance. They arise because galaxies form through consistent physical processes acting on the distribution of matter that exists within each dark matter halo. The formation of a galaxy involves many stages. Gas must fall inward and cool. Stars must form. Gas must continue circulating. Mergers must occur or be avoided. Radiation from stars influences how gas behaves. Supernovae stir and enrich the gas. Supermassive black holes form in the centers of many galaxies, shaping the movement of material in their cores. All of these steps happen gradually, with each stage influencing the next. The universe organizes itself because the rules and conditions consistently guide matter towards stable, long-lived arrangements. Over time, galaxies settled into the large-scale patterns that dominate the universe today. They are not scattered randomly. They appear in clusters and filaments that trace the early fluctuations in density. These structures extend across thousands of millions of light years. Within these large-scale structures, galaxies interact with one another, move along gravitational pathways, and follow the distribution of matter set long ago. The cosmic web reflects the entire history of the universe's development, beginning with tiny fluctuations and eventually leading to the arrangement of galaxies we see today. Even within an individual galaxy, the organization continues developing. Star formation shifts from one region to another. Gas is consumed, enriched, and redistributed. Stars age and change their positions. Some migrate outward or inward depending on gravitational influences. Dark matter continues providing the central gravitational framework, keeping stars and gas bound together. The galaxy remains dynamic over billions of years, constantly evolving within its stable structure. The patterns that galaxies form aren't fragile. They are resilient because they arise from the same underlying laws that shape the universe from the beginning. Those laws guided particles, formed atoms, allowed clouds to collapse, supported starbirth, and continue shaping every level of structure. Galaxies exist because the universe's rules reward stability. Structures that remain stable last long enough to grow, merge, and develop complexity. Planetary systems form within galaxies because the disks around stars follow the same principles as the disks around galaxies. Large structures mirror small ones. Rotation leads to flattened arrangements. Collisions redistribute material. Gas cools and condenses. Over time, planets emerge from these processes. The organization of galaxies makes planetary formation possible because it provides long-term stability in environments where gas can exist in consistent conditions for long stretches of time. As billions of years pass, galaxies continue changing. They lose gas or gain it from interactions with other systems. They merge with neighbors or pass close enough to distort each other through gravitational tides. Some galaxies stop forming stars because they no longer have enough cool gas. Others continue forming stars actively. These differences don't break the overall pattern. They add diversity to the universe without disrupting the stability of the larger structures. When viewed from afar, galaxies can appear as intricate shapes, almost as if they were crafted. But their shapes are natural consequences of the rules that govern matter. Spirals appear because rotation and gravity balance each other. Ellipticals appear because repeated mergers disrupt orderly motion. Irregular shapes appear because some galaxies form in isolated or unstable environments. All of these outcomes reflect the combination of early conditions and long-term dynamics. Galaxies also reveal the presence of dark matter. Their rotation speeds cannot be explained by the amount of visible matter alone. Dark matter contributes additional gravitational influence, keeping stars bound at higher speeds than visible matter would allow. This influence shapes the outer regions of galaxies and contributes to the stability of the galactic disks. Without dark matter, many galaxies would not hold together. Throughout their lives, galaxies serve as the locations where most structure in the universe develops. Stars form, age, and die within them. Planets arise around stars. Elements are created through fusion and released into the surrounding gas. Over time, galaxies become the environments where complex chemistry and eventually life can emerge. Their organization allows stable conditions to persist for billions of years, giving time for processes that require immense durations. Everything that galaxies become, and everything they eventually support, stems from the earliest fluctuations and the rules that shape those fluctuations into large, stable systems. Their spiraling patterns, central bulges, halos, and ongoing cycles of star formation all reflect the gradual organization of matter across scales. As the universe continues evolving, galaxies remain essential components of its structure, extending the patterns that began forming long before the first stars brought light into space. Across everything the universe has built so far in this story, one theme keeps reappearing. The visible matter we can detect directly is only part of the picture. Stars, gas, and dust are important, but they do not provide enough mass to explain how galaxies formed or how they maintain their structure. Their motions cannot be accounted for by the matter we can see. The stability of galaxy clusters doesn't follow from visible mass either. Something else must support the gravitational framework that holds these systems together. Understanding how the universe became structured requires acknowledging that most of the matter involved in shaping these structures cannot be observed with light. This unseen material, dark matter, provides the backbone for nearly everything that formed on large scales. The existence of dark matter became clear through observations rather than speculation. When astronomers measured how stars in galaxies moved, they found that the stars orbited too quickly for the visible mass to hold them in place. In a system where gravity comes only from the matter we can detect, stars on the edges should orbit more slowly. Instead, they move at speeds indicating that far more mass is present than can be seen. The speed does not drop off gradually. It remains consistently high, pointing to a large amount of material extending beyond the visible boundaries of the galaxy. The same effect appears when studying galaxy clusters. These clusters contain dozens or hundreds of galaxies bound together by gravity. When astronomers calculated the total mass required to keep the galaxies from drifting apart, they found that the visible matter in the cluster was not nearly enough Something else had to contribute most of the gravitational pull. This realization led to the conclusion that most of the matter in the universe is not luminous. It doesn't interact with light, it doesn't emit radiation, it doesn't absorb or reflect photons, it only interacts through gravity. Dark matter began influencing the universe long before stars or galaxies existed. In the very early stages, when the universe was still a hot plasma, dark matter had already begun responding to the slight variations in density created by the earliest fluctuations. Because dark matter doesn't interact with radiation, it wasn't pushed outward the way ordinary matter was. Radiation pressure influenced protons, electrons, and photons, but dark matter moved freely under the influence of gravity. This allowed dark matter to gather into structures earlier than ordinary matter could. These structures provided the framework for everything that followed. The earliest dark matter structures grew gradually. Gravity pulled dark matter toward regions that were slightly denser. These regions became increasingly pronounced as more dark matter accumulated. The structures didn't resemble anything like galaxies yet. They were extended halos, diffuse and spread out, containing most of the mass in each region. These halos had no light, no stars, no gas. They were invisible except for their gravitational influence. But because they contained most of the mass, they defined the positions where later structure would form. Once ordinary matter cooled enough to fall into these halos, gas accumulated inside them. The gas moved along gravitational gradients shaped by the distribution of dark matter. It wasn't the gas that determined where galaxies formed. It was the pattern created by dark matter. If a region contained a large dark matter halo, gas flowed into it and formed the earliest galaxies. If a region contained only small halos, smaller galaxies formed. Regions with very little dark matter remained mostly empty. Even the large voids in the universe reflect the distribution of dark matter, not just gas. Dark matter doesn't behave like ordinary matter in several ways. It doesn't clump into stars or planets. It doesn't cool. It doesn't collapse into disks. It remains in large, extended halos, distributing itself based on gravity alone. This means the shape of a galaxy is influenced by dark matter from the moment it begins forming. The visible disk of a spiral galaxy sits inside a much larger dark matter halo. The halo extends far beyond the reach of the stars. It provides the gravitational pull needed to keep the outer parts of the galaxy bound. Without this halo, the galaxy would fly apart. Dark matter halos are not all identical. Their shapes depend on how matter moved during the earlier stages. Some halos became massive quickly. These halos form the centers of large galaxies. Others developed slowly. These halos produce small galaxies or groups of galaxies. The differences in halo size and distribution reflect the earliest fluctuations in density. The architecture of the universe on large scales mirrors the pattern of these halos. Clusters of galaxies appear where dark matter halos were initially dense. Filaments form where halos connected. Voids form where halos were scarce. The influence of dark matter becomes clearer when looking at how galaxies rotate. In a typical galaxy, the stars near the center move more slowly than those farther out. But dark matter creates a gravitational influence that remains strong in the outer regions. This influence prevents the stars from drifting away, holding the galaxy together even where visible matter is sparse. This effect also allows galaxies to maintain their shapes over long periods. Without dark matter, galaxies would be much more fragile. Dark matter also affects the interactions between galaxies. When galaxies approach each other, their dark matter halos overlap long before the visible stars interact. These overlapping halos influence the paths the galaxies take and the way they merge. The stars and gas respond to these gravitational effects, but the halos provide the main influence. Mergers shape the development of galaxies, but the process begins with halos interacting through gravity. The energy exchange between halos determines whether a merger produces a spiral, an elliptical, or an irregular galaxy. Even the cosmic web is shaped primarily by dark matter. The web consists of filaments, nodes, and voids form through the gravitational influence of dark matter. Gas and galaxies simply trace the shapes that dark matter created. When simulations include dark matter and gravity, they naturally produce a cosmic web that closely resembles what astronomers observe. Without dark matter, these simulations fail to produce realistic patterns. The density of dark matter determines where galaxies cluster and how large-scale structures develop. Dark matter influences star formation as well. Gas within a halo cools and falls inward, but the depth of the halo's gravitational well determines how much gas accumulates. A deep well supports continuous star formation. A shallow one leads to small galaxies with intermittent star formation. The size and shape of the halo influence how efficiently gas cools and collects. Regions with massive halos produce galaxies that remain active for a long time. Regions with small halos produce galaxies that form stars only occasionally. The presence of dark matter also helps explain why galaxies of similar size can behave differently. Two galaxies may contain similar amounts of visible matter, but have very different rotation speeds. This difference reflects variations in the distribution of dark matter. Some halos are more concentrated, others are more diffuse. These variations arise from the early conditions in the universe and the history of interactions each halo experienced. Dark matter halos influence the internal structure of galaxies as well. The central region of a halo affects the shape of the galaxy's core. Some galaxies have dense central regions, others have more extended cores. These differences are influenced by the concentration of dark matter. The halo's shape also influences how stars move within the galaxy. Stars follow orbits determined partly by the visible mass and partly by the distribution of dark matter. Dark matter continues shaping galaxies throughout their lifetimes. As galaxies move through space, their halos interact with surrounding dark matter. This influence changes the galaxy's trajectories and can affect the distribution of gas within them. When galaxies pass through clusters, the cluster's dark matter exerts tidal forces that distort the galaxies. These distortions change the way gas flows inside them, influencing star formation. Dark matter provides stability, but it also contributes to long-term evolution. The influence of dark matter extends to the earlier stages of galaxy clusters. Clusters form when dark matter halos merge. These merged halos create deep gravitational wells that can capture many galaxies. The galaxies then move within the cluster, bound by the cluster's dark matter. Gas within clusters reaches high temperatures because it falls into these deep wells. This hot gas emits X-rays and forms a major component of cluster structure. But the shape and size of the cluster depend on the distribution of dark matter. Dark matter also affects how light travels through the universe. Although dark matter doesn't interact with light directly, its gravitational influence bends the path of light. This effect, known as gravitational lensing, allows astronomers to detect dark matter. Light from distant galaxies is bent as it passes through regions with dark matter. The distortions provide a map of the dark matter distribution. These maps show that dark matter forms the backbone of the universe's large-scale structure. Even though dark matter cannot be observed directly, its existence explains many features of the universe that would otherwise remain unexplained. The rotation of galaxies, the stability of clusters, the shapes of large-scale structures, and the growth of early fluctuations all point to the presence of dark matter. Without it, the universe would look very different. Galaxies might not have formed. Clusters might not exist. The cosmic web would not appear in its current form. Dark matter doesn't need to be complex to produce these effects. It simply needs to respond to gravity consistently and avoid interacting strongly with light or ordinary matter. These two properties allow it to form large halos while remaining invisible. The halos shape the universe in ways that reflect the early fluctuations and the rules governing gravity. Ordinary matter follows the paths created by dark matter, gathering into structures that continue evolving. Understanding how the universe manages to create stable structures requires looking at more than gravity, gas, and dark matter. Those ingredients are essential, but they don't fully explain why the universe develops patterns instead of dissolving into complete disorder. Matter doesn't behave quietly all the time. Gas clouds move unevenly, galaxies collide, stars form in bursts and stop forming in other regions. Temperature shifts create turbulence. Collisions scatter material across large distances. On smaller scales, particles move unpredictably, and on larger scales, galaxies drift through different environments. Yet, despite all these unpredictable influences, the universe maintains long-term order. Patterns persist. Structures remain stable for billions of years. The existence of order in a universe with so many opportunities for disorder comes from a balance between processes that create variation and processes that stabilize that variation. To see how this balance operates, it helps to begin with the recognition that the universe is not a static place. Everything moves, everything interacts, every part of the universe experiences forces that push, pull, or redirect matter. Gas in galaxies flows under gravitational influences, but also responds to pressure and temperature. Stars orbit in patterns influenced by the distribution of mass around them, but occasionally experience encounters that alter those orbits. Even in regions that appear calm, such as the vast spaces between galaxies, material still moves slowly through gravitational paths set long ago. The universe never stops changing, yet these changes don't erase the larger structures that formed. One reason for this stability is that the physical laws governing matter do not fluctuate. The forces that act on everything remain consistent. Gravity does not change its behavior from one moment to the next. Atomic interactions follow the same rules regardless of location. Temperature influences motion in predictable ways. Even when matter behaves unpredictably on small scales, the outcomes still fall within boundaries defined by these rules. That consistency allows order to emerge because matter cannot stray too far from the patterns enforced by the laws of physics. However, consistency alone is not enough. The universe also needs variation. Without variation, structure cannot form. If the early universe had been entirely uniform, gravity would have produced no clumps. Without differences in temperature or density, gas would not collapse into stars. Without variations in motion, galaxies would not develop the rotation needed to form disks. Variation introduces randomness that allows structures to diverge, evolve, and take on unique shapes. This is where the balance forms. Variation provides the differences that structures grow from. Consistency provides the limits that prevent variation from destroying everything. On small scales, this balance appears in the behavior of gas clouds. Gas does not collapse smoothly. It moves unevenly because temperature, pressure, and collisions prevent uniform behavior. These irregular movements create pockets where gas becomes denser, and pockets where it becomes less dense. If the cloud were perfectly calm, it would collapse too quickly or not at all. The turbulence slows collapse in some places and encourages it in others. Without turbulence, star formation would not follow the patterns it does. Too much turbulence would prevent collapse entirely, scattering gas before stars could form. The balance allows some regions to collapse while others do not, setting the stage for clusters of stars and regions that remain quiet. A similar pattern appears in the motion of stars inside galaxies. If stars orbited perfectly without disturbances, their movement would be simple and predictable. But galaxies contain many stars, and each contributes its own gravitational influence. Stars occasionally pass close enough to one another to alter orbits slightly. These changes accumulate over long periods. The motions appear complex, but they remain bound by the gravitational field of the galaxy. These interactions help prevent overly rigid behavior, which could destabilize the system. While not being chaotic enough to break the structure apart, the galaxy remains stable because the overall gravitational structure keeps stars in orbit even as they experience small, irregular influences. On larger scales, galaxies themselves behave in ways that reflect this balance. Galaxy mergers are not orderly events, They involve complicated interactions as stars, gas, and dark matter influence one another. Gas moves into new orbits, stars are pulled into different paths, and some material is ejected. These interactions seem chaotic, but the result often leads to stable galaxies. An elliptical galaxy forms when two spiral galaxies merge. The merger appears disruptive, but the new system remains coherent because gravity establishes a new equilibrium. Too much disruption would scatter the material beyond recovery. Too little variation would result in structures that never evolve. The universe manages to remain stable, while still allowing enormous collisions to reshape galaxies. The distribution of galaxies in the universe also depends on a mixture of order and variation. On large scales, the cosmic web appears organized, with filaments connecting clusters. But within those filaments, galaxies are scattered unevenly. Some areas contain many galaxies, others contain only a few. These differences reflect the initial fluctuations in density, but the overall pattern remains consistent. The cosmic web doesn't dissolve into complete randomness because gravity holds the larger structure together. At the same time, it doesn't become perfectly symmetrical because variation prevents uniform outcomes. Each region develops in its own way based on its initial conditions and later interactions. Another example of this balance appears in the behavior of dark matter. Dark matter halos form because dark matter accumulates in areas of slightly greater density. The halos don't collapse completely because dark matter doesn't cool. It remains spread out, providing a stable gravitational influence. Within the halos, ordinary matter can collapse into stars and galaxies. Dark matter does not produce fine structure, but it creates the conditions for ordinary matter to develop structure within stable gravitational environments. The interaction between these two forms of matter demonstrates the balance between underlying stability and local variability. Temperature variations also contribute to this interplay. When gas cools, it collapses. When it heats, it expands. Temperature gradients create movement and turbulence, but also limit the conditions under which collapse can occur. Too much heat prevents structure. Too little variation would lead to overly rigid behavior. The range of temperatures present in different environments keeps matter moving enough to form new structures while preventing collapse that would destroy existing ones. Even the life cycles of stars add to the balance. Stars produce energy through nuclear fusion, which counteracts gravity. As stars age, their internal structure changes. Some expand, some contract, some explode. These changes affect their surroundings. When a massive star explodes, it sends shock waves through nearby gas. The shock waves compress certain regions, promoting star formation. They disperse gas in other regions, halting star formation. The result is a mixture of order and disruption. The explosions don't destroy the galaxy, they help regulate its development. Without these disruptive events, star formation would be too uniform, creating structures that might collapse under their own weight or fail to evolve. On even larger scales, galaxy clusters provide a clear picture of ordered structure coexisting with complex interactions. Clusters contain many galaxies orbiting within a shared dark matter halo. Their motions appear chaotic when viewed individually, but the overall cluster remains stable. The cluster does not fall apart because the gravitational influence of the dark matter halo keeps the galaxies bound. The galaxies do not follow simple, predictable orbits, but they remain within the cluster. This behavior results from the balance between gravitational influence and the varied motions of the galaxies. The large-scale evolution of the universe also reflects this balance. The expansion of the universe creates increasing distance between regions, spreading matter out. Without gravity, the expansion would erase structure, but gravity slows expansion in dense regions, allowing structures to form. The expansion prevents everything from collapsing into one massive structure. Gravity prevents everything from dispersing completely. The result is a universe where structure can continue growing within expanding space. This balance even influences how long structures survive. Galaxies can remain stable for billions of years, because the forces acting on them remain within certain limits. Too many disruptive events would break them apart. Too few would prevent their development. Temperature differences, motion, interactions, and distribution of matter combine to create long-term stability without eliminating variation. This long-term stability is necessary for the growth of planetary systems and the environments within galaxies that allow complex chemistry to occur. The behavior of gas inside galaxies highlights the importance of this balance. Gas can collapse to form stars, but only when it cools enough. Gas can also be heated by radiation or shock waves, preventing collapse until conditions change. This cycle keeps star formation from proceeding uniformly across the galaxy. Instead, it occurs in waves or regions shaping the structure of the galaxy over time. Variation prevents uniform collapse, while stability prevents the gas from dispersing entirely. Another layer appears when considering the movement of stars through the galaxy. Stars migrate because of gravitational interactions with gas and with other stars. These interactions can move stars from the inner regions toward the outer regions or in the opposite direction. Migration doesn't break the galaxy. It redistributes material. This redistribution contributes to the long-term evolution of the galaxy. The structure remains coherent even as individual components change positions. The influence of dark energy adds another dimension to the balance. Dark energy accelerates the expansion of the universe. If dark energy were much stronger, structures might not have formed at all. If it were much weaker, the universe might have collapsed into dense formations without the large-scale patterns we see. The current level of dark energy allows expansion to continue, while still permitting gravity to form and maintain structure. The universe develops patterns because the expansion rate and gravitational strength fall within a range that supports long-term stability. Even at the smallest scales, the rules of physics enforce boundaries that allow order to emerge. Particles cannot move arbitrarily. They follow quantum rules that define the probabilities for certain outcomes. These rules ensure that atoms form, molecules remain stable, and interactions produce consistent effects. If these rules were different, matter might behave unpredictably. Instead, particles follow consistent patterns, allowing complex structures to form even though individual events can be random. Throughout the universe, this balance between variation and stability appears at every level. It allows cloud fragmentation, star formation, galaxy rotation, large-scale structure formation, and cosmic evolution. None of these processes require perfect order. None require complete randomness either. They thrive in the space between. They develop because the universe maintains conditions where variation can produce new possibilities, while stability preserves long-term structures. Looking at how the universe forms its structures, it might seem puzzling that order becomes so common when one of the most fundamental principles in physics describes the natural tendency of systems to move toward states with less organization. This principle, known as entropy, often gets described as a measure of disorder. When people hear that, they sometimes imagine that rising entropy should erase patterns, undo structure, and make the universe drift toward uniformity. Yet the universe contains galaxies, stars, planets, and complicated interactions that grow even more detailed over time. Rather than wiping out structure, entropy plays a role in shaping it. Understanding this requires looking closely at what entropy actually describes and how its influence connects with the processes that drive organization. Entropy describes the number of ways a system's components can be arranged, while still being consistent with the system's overall properties. It reflects the likelihood of certain arrangements, not a preference for chaos over order. When systems evolve, they move towards states with more possible configurations, because those states are statistically favoured. In many everyday situations, this makes things seem more disorganized. Heat spreads from a hot object into a cooler one, because there are more possible arrangements in which energy is evenly dispersed than in which it remains concentrated. A drop of dye spreads throughout water because there are more ways for its molecules to distribute than to remain clustered together. These familiar examples often make entropy feel like a force trying to break down patterns. But the deeper truth is that entropy is not a destructive agent. It is a measure of how energy and matter naturally distribute themselves. The early universe began in a state that appears extremely ordered. Matter and energy were nearly uniform. The temperature was almost the same everywhere, and the distribution of density contained only tiny variations. That uniformity might look like low entropy at first, but the presence of gravity changes the meaning of order. In a system where gravity is important, a uniform distribution of matter is actually a high entropy state, because it allows many possible arrangements without requiring matter to be in any particular configuration. Gravity makes clumps improbable unless the system evolves. As matter begins to gather under gravity, the number of possible states grows because gravitational collapse releases energy. That released energy spreads outward, making it possible for the overall entropy of the system to increase even as matter forms more concentrated structures. This point is important because it means that the formation of stars and galaxies does not violate the principle of increasing entropy. When gas collapses into a star, the collapse reduces the entropy of the gas itself by creating a more concentrated structure. But as the gas collapses, it heats up, and the star radiates energy outward. The radiation increases the entropy of the surrounding environment by an amount that outweighs the decrease inside the star. The total entropy increases, which means the process is fully consistent with thermodynamics. This is one of the reasons the universe can form ordered structures while still following the principle that entropy must rise. When thinking about entropy and structure, it helps to look at examples in which energy flow creates stable organization. A star remains structured because nuclear reactions in its core generate energy that flows outward. The outward energy maintains the star's stability. Without that energy flow, gravity would collapse the star. The star exists in a constant state of maintaining balance by radiating energy. This steady release increases entropy. The star is not defying disorder, it is producing it. The order we see in the star is a part of a larger process that generates more disorder around it. Planets, including those that eventually host conditions for life, also form within this framework. Planets develop when dust and gas in a disk surrounding a young star collide and stick together. These collisions release heat, and the heat disperses into the surrounding environment. The resulting planet is a lower entropy structure compared to the initial dust cloud, but its formation was accompanied by processes that increased entropy overall. The planet remains cold and stable, radiating small amounts of energy into space. These processes fit within the larger trend of increasing entropy in the system as a whole. Even life follows this pattern. Living organisms maintain structure by consuming energy from their surroundings. They use energy to build complex molecules, maintain temperature differences, and power movement. But they also release heat back into the environment. The heat they release increases entropy in the surroundings, more than their internal processes reduce it. Life exists because it is part of a larger system moving toward higher entropy. This is not a violation of thermodynamic laws. It is an example of how ordered structures can arise when energy flows through systems. On the scale of galaxies, entropy also plays an important role. When gas falls into a dark matter halo, gravitational collapse releases energy. The gas heats up as it loses potential energy. That heat must be radiated away for the gas to cool and form stars. The radiation increases the entropy of the surroundings. Meanwhile, the collapse of gas increases the structure within the halo. The overall result is a net increase in entropy. This is how galaxies continue forming stars for long periods. They rely on the cooling of gas, which releases energy and maintains the process of increasing entropy while allowing localized order to develop. Entropy also influences the behavior of galaxy clusters. These clusters contain large amounts of hot gas that emit X-rays. The gas remains hot because it has fallen into deep gravitational wells created by dark matter. The energy released during this fall increases entropy, but the gas stays warm enough to prevent rapid collapse. The cluster remains stable because the energy balance between gravitational potential and thermal energy keeps the gas in a long-lived high-entropy state. The galaxies inside the cluster continue orbiting within the dark matter halo. The overall structure remains intact even though entropy within the cluster continues rising. Another aspect of entropy's role in structure formation emerges when considering how energy spreads out. Systems that experience continuous energy flow often develop stable patterns. These patterns are not the result of entropy decreasing. They are the result of entropy increasing in a way that allows matter to organize temporarily. A classic example in physics is fluid convection. When a fluid is heated from below, the fluid can form stable, repeating patterns of motion. These patterns appear because they transport heat more efficiently. They raise the rate at which entropy increases. The appearance of structure is a consequence of the system finding a pathway to increase entropy more effectively. Some processes that appear to increase organization actually exist because they help the system move toward a higher overall entropy state. This is one of the reasons the universe contains so much structural variation. The formation of stars, the development of galaxies, and the emergence of complex environments occur because these arrangements allow energy to flow in ways that increase entropy more quickly or more widely than a uniform state would permit. Structures emerge to support the processes that raise entropy. Entropy also influences the fate of stars. When a star runs out of fuel, its core collapses. The collapse can create dense objects such as white dwarfs, neutron stars, or black holes. These objects are extremely ordered in the sense that their matter is compressed into small regions, but the collapse that forms them releases vast amounts of energy, increasing entropy dramatically in the surrounding environment. The star's overall entropy outcome, including both the collapse and the radiation it produces, follows the trend of rising entropy. The ordered remnant remains because the processes producing it contributed to a greater increase in entropy elsewhere. In the case of black holes, the relationship between entropy and structure becomes even more striking. Black holes are regions where gravity is so strong that nothing, not even light, can escape. Although they appear simple and featureless, black holes have entropy associated with the area of their event horizons. This entropy is enormous. A black hole's entropy exceeds the entropy of any other object of similar mass. Black holes represent some of the highest entropy structures known. This means that even though black holes appear ordered, their existence supports the trend toward higher entropy in the universe. The role of entropy becomes clearer when thinking about how the universe changes over time. As the universe expands, matter becomes more spread out. Expansion alone increases entropy because it creates more possible arrangements for matter and energy. At the same time, gravity causes matter to collapse in local regions. These collapses decrease entropy locally, but increase it in the environment through energy release. The expansion and the collapse work together to produce a universe with both increasing entropy and increasing structure. This balance allows the universe to maintain organization across many scales. The large-scale structure remains stable while the contents of galaxies evolve. Stars form, live, and die. Gas circulates, planets develop. The universe does not move toward uniformity in terms of visible structure, even though entropy rises. Instead, entropy's rise supports the formation of structures that help distribute energy more efficiently. Another important part of the story involves the flow of time. Entropy defines the direction in which time seems to move. We experience time because systems move towards states with more possible configurations. The early universe had fewer possible configurations than the universe does now. As time progresses, entropy increases. Structures form within this framework, linking the evolution of the universe to the thermodynamic processes guiding it. Many of the structures we observe today exist because they help move the universe toward higher entropy. Galaxies continue forming stars, but star formation slows as gas becomes more dispersed. Eventually, the universe will reach a state where stars no longer form, but entropy will keep rising as stars fade, gas spreads out, and black holes merge or evaporate. The universe's long-term evolution is shaped by entropy, not because entropy removes structure, but because it sets the framework for how structure arises and how it eventually changes. Entropy does not oppose structure. It shapes how structure forms and evolves. It encourages processes that release energy, spread heat, and move matter into configurations with more possible arrangements. The detailed structures that appear along the way exist because they serve as pathways to increase entropy. As we move further into the story of how structure forms on the larger scales, a new picture starts to come into focus. Earlier stages showed how stars form inside dense clouds, how galaxies take shape inside dark matter halos, and how gravity influences the evolution of matter across time. But none of these pieces tells the full story on its own. When astronomers look at the universe across the greatest distances, they see a pattern that spans billions of light years. Galaxies do not scatter randomly. They gather into long chains, broad sheets, and tightly packed clusters. These enormous formations, taken together, create something that resembles a network stretching across the whole universe. This network is often called the cosmic web. Understanding how it formed requires looking at how matter behaved not just within individual galaxies, but across huge regions where gravity, gas, and dark matter all shaped the distribution of everything present. The cosmic web takes shape from the earliest fluctuations in density that existed shortly after the universe began expanding. These small fluctuations were enough for gravity to act on, even though they were extremely slight. Regions with a little more matter pulled in surrounding material. Regions with less matter gradually emptied out as matter moved away. Over time, these small differences grew into large contrasts. Dense areas continued gaining mass, while less dense areas became voids. This process unfolded steadily because gravity amplified the variations. It did not require specific directions or uniform motions. It only required that some areas contained slightly more matter than others. As the universe expanded, the distance between these regions increased, but gravity remained effective on large scales. Expansion made the universe larger, yet it did not prevent matter from gathering along regions where dark matter was already accumulating. The earliest dark matter halos, tiny by modern standards, merged with others, forming larger halos. Over extended periods, halos that were aligned in certain regions created elongated structures. These structures did not form instantly or intentionally. They emerged as a natural result of how matter moved in response to gravity while the universe continued expanding. Gas followed the same gravitational patterns, but experienced additional influences. While dark matter responded only to gravity, gas experienced heating, cooling, collisions, and pressure changes. These processes slowed or redirected gas at times, but the overall pattern still matched the shape dark matter established. Gas settled into the same large-scale structures as dark matter, because those structures contained the deepest gravitational wells. Even though gas behaved differently from dark matter in many ways, its average movement aligned with the pattern formed by the halos. As time passed, the density differences became more dramatic. Regions with abundant dark matter attracted gas more effectively. These areas eventually developed into the large filaments of the cosmic web. Filaments are long, thin structures filled with dark matter, gas, and galaxies. They stretch across enormous distances and link together nodes where several filaments meet. These nodes contain the densest concentrations of matter in the universe, often hosting massive clusters of galaxies. The filaments feed these clusters by funneling gas and galaxies toward them through the steady pull of gravity. Inside these filaments, galaxies move along pathways shaped by the dark matter distribution. They do not drift randomly. Their motion is guided by the gravitational landscape. When astronomers map the positions of galaxies across wide regions of sky, they see these long filaments clearly. The galaxies trace the shape of the dark matter, even though the dark matter itself cannot be seen directly. Observations of gravitational lensing confirm that dark matter is present in the same places where the filaments appear. This alignment shows how the cosmic web is anchored by dark matter, while the visible matter simply fills in the pattern. The formation of the cosmic web is not only a story of gravity pulling matter inward, it also involves the expansion of the universe, which stretches the distances between structures. Expansion makes it harder for matter to collapse on the larger scales, but within regions where the density is high enough, gravity still dominates. These regions grow into filaments and clusters because their densities exceed the critical threshold required for collapse. In regions where the density is below that threshold, expansion wins. Matter becomes more spread out, forming vast voids. These voids can stretch for hundreds of millions of light years and contain only a few galaxies. The contrast between dense filaments and empty voids is one of the defining features of the cosmic web. On smaller scales within the web, galaxies form groups, clusters, and superclusters. In clusters, galaxies orbit within a shared dark matter halo. Many clusters contain hot gas that emits X-rays, showing how much matter has fallen into these deep gravitational wells. The gas remains hot because the gravitational energy released during collapse raises its temperature. This hot gas is another indicator of the cosmic web's formation. It shows where matter has gathered most intensively, and how energy has distributed itself during the process. In some regions, filaments connect several clusters. These connections act like bridges of matter between the most massive structures. Galaxies travelling along these filaments often move toward clusters, contributing to their growth. When galaxies reach a cluster, they may experience tidal forces, interactions with hot gas, or close encounters with other galaxies. These influences change the galaxy's shapes, star formation rates, and gas content. The cosmic web not only organizes galaxies across large distances, but also affects how galaxies evolve when they reach different environments. Gas within the filaments behaves differently from gas inside galaxies. It remains diffuse and warm, filling the spaces between galaxies. This gas contains clues to the universe's early development because it has not yet collapsed into stars or dense clouds. Some of this gas eventually cools and flows into galaxies, supporting star formation. In other cases, it remains part of the large-scale structure, without contributing directly to galaxy growth. The presence of this gas shows how the cosmic web supports continued development by providing reserves of material that can feed galaxies for billions of years. The shapes of filaments reflect the initial distribution of matter. Some filaments are straight, others curve or branch. The pattern is determined by the fluctuations present near the beginning of the universe. Filaments form where the density was slightly higher than average but not high enough to collapse into clusters immediately. Over time, gravity enhanced the small differences, turning them into long structures. The web's appearance reflects how matter followed the path of least resistance, while responding to gravitational forces acting across vast distances. Dark matter simulations provide one of the clearest views of how the cosmic web forms. When physicists simulate the early universe with dark matter as the primary component, they obtain a structure that closely matches observations. Gas and stars added to the simulations follow the same patterns. This alignment shows that the cosmic web shape is not random. It arises naturally from the rules governing gravity and the distribution of initial fluctuations. The web's features, filaments, nodes, and voids, appear whether or not visible matter is included. They arise because dark matter dominates the gravitational field on the larger scales. The cosmic web is not static. It continues evolving as galaxies move, gas flows, and structures merge. Filaments can direct matter toward clusters, increasing their mass over time. Clusters can merge, forming even larger structures. Voids can grow as matter flows out of them. These processes create slow adjustments to the web, maintaining the overall pattern while reshaping the details. The web's large-scale structure remains stable because gravity continues guiding matter along the same paths, even as individual galaxies shift positions. As galaxies move within the web, their interactions with the surrounding environment shape their development. Galaxies in dense regions experience frequent encounters, heating of their gas, and the removal of material through tidal forces. These effects can reduce star formation. In contrast, galaxies in filaments or near voids often retain more gas and continue forming stars over longer periods. The position of a galaxy within the cosmic web influences its entire history. It determines how often it encounters other galaxies, how much gas it can draw from its surroundings, and how its structure evolves over billions of years. On even larger scales, the web shapes how matter flows across the universe. Filaments guide gas into clusters. Clusters anchor the nodes. Voids expand as matter drains into the surrounding filaments. Expansion of the universe stretches all these regions, but gravity keeps the densest areas connected. This interplay maintains the overall pattern of the web. The result is an arrangement that remains recognizable across enormous distances. One of the most interesting aspects of the cosmic web is that it reveals how structure emerges even when the universe appears mostly empty. Voids contain very little matter, yet they influence the movement of galaxies along their edges. The presence of emptiness contributes to the contrast that defines the web. The space between filaments makes the filaments themselves more pronounced. The absence of matter becomes part of the structure, creating boundaries that shape the arrangement of the visible universe. Another feature of the cosmic web is the way it connects the earlier stages of the universe to the structures we see today. The fluctuations present shortly after the beginning became magnified through gravity and expansion. These fluctuations determine the positions of the filaments and voids. The cosmic web acts as a record of those early conditions. By studying its shape, scientists learn about how the universe behaved during its first moments. The web is a three-dimensional map of how matter responded to the earliest differences in density. When we shift attention from the largest structures in the universe to the smallest environments where matter organizes itself, the scale changes dramatically, but the underlying principles continue following the same rules. Stars, galaxies, and cosmic webs may feel distant and enormous, yet the basic mechanisms that shape them also appear in the formation of planets, the chemistry within their surfaces, and eventually in the emergence of complex systems that behave differently from the inanimate material around them. Life becomes one example of how structure can grow out of smaller patterns, not because the universe makes special exceptions for it, but because the same conditions that support the development of galaxies can, on much smaller scales, support the development of systems that maintain order by exchanging energy with their surroundings. Life emerges as an outcome of natural processes acting on matter, allowing tiny worlds to become places where structure reaches a level of detail that cannot be replicated on cosmic scales. The story begins long before any living system appeared. Planets formed within disks of gas and dust surrounding young stars. These disks contained material left over from star formation, shaped by collisions, motion, and the gravitational pull of the star. Dust grains collided, sticking together in ways determined by electrical forces and mechanical interactions. Over time, these grains grew into larger objects. Collisions continued, some destroying material and others merging objects into bigger ones. As these larger bodies formed, they became planetesimals. These planetesimals interacted through gravity, drawing in nearby material or colliding with one another to form larger structures. Eventually, some of them grew into full planets. Planets inherited the composition of the disk they formed from. Some became rocky worlds, while others accumulated enough gas to become giant planets. Their distance from the star determined their temperature. The temperature in turn determined which materials remained solid or gas. These simple factors shaped the environments on the planet's surfaces. On rocky planets located at distances where temperatures allowed liquids to exist, the combination of solid surfaces, atmospheres, and flowing energy formed the conditions that would later allow life to emerge. These conditions were not rare in principle. They resulted from physical laws acting in predictable ways. Any star with a disk of material has the potential to form planets. Any planet with the right composition and temperature can support chemical reactions. These steps require no unusual events. Chemical complexity becomes possible when matter interacts through repeated cycles of heating, cooling, mixing, and separation. On early rocky planets, chemical reactions occurred between minerals, water, gases, and energy sources such as sunlight or geothermal heat. These reactions did not form complex molecules instantly. They formed gradually, producing small organic compounds that could interact further. Some dissolved in water, others attached to mineral surfaces, some broke apart again. Over time, repeated reactions created more complex structures. These processes continued because the environment supported them. Water circulated, carrying dissolved materials to new locations. Temperature differences created cycles that allowed reactions to occur at different rates. Surfaces provided platforms where molecules concentrated. At this stage, the formation of complex molecules was driven by natural chemical behavior. Molecules with stable structures persisted. Molecules with unstable structures broke apart. Reactions that occurred easily continued. Reactions that required unusual conditions remained rare. These predictable patterns guided chemical evolution without requiring any direction. As long as energy flowed into the environment and the system remained open, more complex arrangements of matter could develop. Eventually, certain molecules appeared that could store information in their structure. These molecules could interact with each other in ways that allowed them to copy aspects of their shape or function. They did not replicate perfectly at first. They formed variants that behaved differently. Some variants persisted longer, others disappeared. This early form of information storage allowed chemical systems to begin behaving in ways that supported more complex interactions. Molecules that could catalyze reactions helped produce more of themselves. Molecules that formed protective structures lasted longer in hostile environments. Variations allowed the system to grow beyond simple chemistry. None of these early steps violated the natural trend of increasing entropy. The formation of complex molecules required energy. That energy came from the environment and was eventually released as heat, which increased entropy overall. The local reduction in entropy within the molecule was offset by the larger increase in entropy around it. This pattern continued as complexity increased. The environment provided the energy flow, and the chemical systems used the energy to maintain structure. The structure existed because it contributed to a larger system moving toward higher entropy. Over time, collections of molecules began interacting in ways that supported more stable arrangements. These early systems may have formed inside small compartments, such as mineral pores or droplets. Compartments created boundaries that prevented molecules from dispersing immediately. They allowed chemical reactions to occur in concentrated environments rather than diluted ones. These boundaries were not living membranes yet, but simple structures that kept chemicals together. Inside these compartments, networks of reactions could cycle more efficiently. These cycles gradually grew more complex, enabling new processes to occur. Eventually, some compartments developed membranes made of molecules that naturally assembled into barriers. These barriers allowed certain molecules to enter or leave while keeping others inside. As reactions continued, membranes became important for maintaining internal environments. The internal conditions could differ from the external surroundings. This difference supported reactions that would not occur freely in open environments. Maintaining these conditions required continuous energy flow. Without energy, the system would break down. With energy, it could grow more complex. The next major step involved systems that could copy themselves more reliably. Replication allowed information to guide the structure and function of the system. Variation still occurred during replication, creating differences among systems. Some variants operated more efficiently, some survived external stresses better, some processed energy more effectively. These differences influenced which systems persisted and which ones failed. Over time, selection favoured systems with greater stability and more effective replication. This process laid the foundation for biological evolution. Life began when these replicating systems developed the capacity to maintain internal structure, to store and use information, and to interact with their environment in ways that supported long-term persistence. This transition did not happen in a single step. It happened through countless small changes shaped by chemical interactions and energy flow. Each step produced a slight increase in complexity. None required events that fall outside the behavior of natural systems. The same principles that guide star formation and galaxy evolution, variation, structure, energy flow, and stability, guided the emergence of life. Once life appeared, it influenced its surroundings. Early organisms used the energy available on their planets in ways that changed the chemical environment. Some released gases, some altered mineral surfaces. These changes affected other organisms, creating feedback loops that made the environment more dynamic. Life interacted with non-living processes, shaping the planet's structure in new ways. The planet became a coupled system, where geological processes and biological processes affected each other. Over billions of years, life diversified. Different environments supported different forms. Some organisms thrived in shallow water, others adapted to deep oceans or volcanic vents. Some lived in soil or on rocky surfaces. Each environment provided resources, and each organism used them according to its internal structure. The structure of life remained tied to the flow of energy. Organisms used sunlight, chemical gradients, or heat to maintain their internal order while increasing entropy around them. This connection between order and energy flow continued throughout biological evolution. Life expanded across the surface of planets that supported it. The presence of life altered the atmosphere by introducing new gases. These changes affected temperature, climate, and chemical composition. Over time, these effects reshaped the planet. The structure of the planet, its oceans, atmospheres, and surface chemistry, became strongly linked to the structure of life itself. This interplay shows how small-scale organization can influence larger-scale patterns. Even though life appears complex, the principles behind its development are straightforward. Variation allows differences to arise. Energy flow maintains structure. Selection favors systems that use energy effectively. These same principles shape everything from star formation to galaxy evolution. Life is not separate from the universe's tendency to create structure. It is one manifestation of how matter organizes under certain conditions. As life becomes more complex, the structures it forms become more detailed. Cells organize into tissues. Tissues form organs. Organs form organisms. Communities form ecosystems. Each level builds on earlier levels. Each requires energy to maintain. The structure at each level supports processes that raise entropy in the surrounding environment. This connection means that life fits comfortably within the physical laws governing the universe. Even the emergence of intelligence follows the same framework. Brains develop because they support information processing that enhances survival. Intelligence allows organisms to respond to environmental changes more effectively. This response increases the chances of persistence. The structure of neural networks emerges because they facilitate energy-efficient information transfer. These patterns develop through biological evolution, not because of exceptions to natural laws, but because the conditions support increasing complexity when energy flows through well-organized systems. When viewed from a cosmic perspective, life may appear small in scale compared to galaxies or galaxy clusters, but the processes that allow life to exist reflect the same principles that shape the larger structures. Gravity organizes matter on cosmic scales. Chemistry organizes matter on planetary scales. Biology organizes matter within narrow environmental boundaries. All of these forms of organization require differences, energy flow, and stability over time. Life continues evolving as long as environments support the flow of energy. Changes in climate, geology, or radiation levels influence which forms of life persist. These changes do not eliminate the structure of life, they alter it. When conditions shift, life adapts or moves, maintaining its presence through variation and selection. The structure of life remains dynamic because it depends on processes that never stop changing. The emergence of life reveals that the universe's capacity to create structure extends far beyond stars and galaxies. Even on small worlds orbiting ordinary stars, matter can organize into systems capable of preserving information, interacting with their surroundings, and forming new layers of structure. Trying to understand why the universe contains structure at all brings us to a point where the questions grow larger than the objects we've been examining. Up to now, the focus has been on how stars form, how galaxies grow, how dark matter shapes the cosmic web, and how small-scale systems such as planets and living organisms create order through natural processes. These explanations reveal how structure behaves and how it develops, but they do not directly explain why the universe ended up with conditions that allow structure in the first place. They show that once small differences exist, gravity amplifies them. They show that energy flow supports complex arrangements. They show that matter responds predictably to the rules that guide it. Yet none of this fully addresses why the universe is structured instead of featureless. Exploring this requires looking closely at the properties of matter, the behavior of the forces acting on it, and the starting conditions that shaped everything moving forward. One of the first things to recognize is that structure becomes possible only because matter interacts. If matter did not respond to forces, no patterns could form. Gravity is essential because it influences every particle with mass, no matter how far apart those particles are. Without gravity, the universe would remain a loose collection of particles drifting endlessly. Nothing would gather. Nothing would collapse. Nothing would change direction. The presence of gravity means that any slight difference in density leads to movement. Matter flows toward regions with greater mass. Over long periods, these flows create concentrated structures. Gravity supplies the mechanism that turns differences into patterns. But gravity is not the only force that makes structure possible. The electromagnetic force plays an equally important role on smaller scales. It allows atoms to form by binding electrons to protons. It allows molecules to form from atoms. It allows matter to solidify into surfaces and dissolve into liquids and gases. Without the electromagnetic force, matter would not remain stable. The smallest building blocks of structure would not exist long enough to combine into larger systems. The electromagnetic force also supports energy flow, which is essential for maintaining structures once they appear. Stars shine because electromagnetic interactions release energy. Planets maintain atmospheres because the force binds molecules together. Life uses electrical and chemical interactions to carry out reactions. Another component behind the existence of structure is the way matter behaves under different temperatures and densities. When the universe was extremely hot and dense, matter behaved as a high-energy plasma. At those temperatures, atoms could not form. No stable structures were possible. As the universe expanded and cooled, matter changed its behavior. The temperature dropped enough for electrons to join with protons, creating atoms. This transition allowed light to travel freely and allowed gas to respond more directly to gravity. Without cooling, matter might have remained too energetic to collapse into stars or galaxies. Cooling provided the conditions that made structure possible on larger scales. The balance between expansion and gravity also plays an important role. If the universe expanded much faster than it did, matter would have spread out too quickly for gravity to bring it together. If expansion proceeded too slowly or failed to occur, matter might have collapsed into dense clumps before any stable structures could develop. The balance between these effects determines how structure appears. Expansion spreads matter apart, preventing immediate collapse. Gravity draws matter together, encouraging collapse where densities are high enough. Together they produce a universe where structures can grow gradually, rather than forming all at once or failing to form at all. Another reason structure exists is that the early universe contained slight fluctuations in density. These fluctuations were tiny, but they were essential. Without them, gravity would have had nothing to act upon. A perfectly uniform universe would remain uniform. Gravity would have no preferred direction or region to pull matter toward. The fluctuations gave gravity a starting point. Their presence allowed matter to gather slowly, forming the seeds of later structures. These fluctuations came from quantum processes that occurred when the universe was extremely young. They were not arranged intentionally. They arose from the nature of particles at very small scales. The existence of matter itself depends on properties that support structure. Matter is stable because particles such as protons and electrons remain intact for long periods. Their stability allows atoms to persist. If these particles decayed quickly, atoms would not form. If the strengths of the fundamental forces were different, atoms would not hold together. If the masses of particles differed significantly, chemical interactions might not occur. These properties allow matter to combine into complex arrangements and remain that way. They make structure feasible. On larger scales, dark matter provides additional support. Without dark matter, gravity from visible matter alone might not be strong enough to form the large-scale structures we observe. Galaxies might not gather into the shapes they have. Filaments and clusters might not appear. Dark matter strengthens the gravitational skeleton of the universe. It does not form atoms or stars, but it shapes the environment in which they arise. Its presence ensures that gravity has enough influence to counteract expansion in regions dense enough to form structure. Beyond the presence of forces and particles, the universe also maintains certain properties that support long-term structure. One of these is the uniformity of physical laws. The laws governing matter and energy apply the same way everywhere. They do not fluctuate depending on location. This consistency ensures that the same interactions that formed atoms in the early universe also support star formation billions of years later. Structure depends on reliability. If the rules changed unpredictably, matter might not behave in ways that allow stability. Consistency allows processes to repeat across vast regions and time periods, enabling structure to arise and persist. Energy also plays an essential role in creating and maintaining structure. Stars form because gas clouds lose energy by radiating heat into space. Planets remain stable because they radiate heat and experience energy flow from their parent stars. Life persists because it processes energy from its environment. Energy flow prevents systems from reaching motionless equilibrium. Without flow, systems would become static and unable to maintain structure. Energy provides the means for complex systems to remain organized even though their surroundings move toward higher entropy. Another factor behind the existence of structure is that systems capable of maintaining organization tend to persist longer than systems that cannot. This idea does not imply a purpose. It simply reflects the fact that stable structures last while unstable ones do not. Stars that maintain internal balance shine for long periods. Atoms that remain bound persist. Molecules that resist breaking apart accumulate. Planets that remain intact continue orbiting. Over long periods, the universe becomes filled with stable structures, because unstable ones either fall apart or transform into stable forms. This gradual filtering process contributes to the presence of organized matter. It is also important to consider that structure arises because the universe is not perfectly balanced. Differences exist. Temperature varies. Density varies. Motion varies. These differences provide the conditions that drive structure formation. If everything were identical everywhere, no structure would ever develop. Uniformity suppresses growth. Variation supports it. Even the smallest differences become important when gravity amplifies them, or when energy flows through systems. Over long timescales, small variations produce large outcomes. Structure appears because differences never disappear entirely. Examining why these differences exist leads back to the earliest moments of the universe, when quantum fluctuations occurred at scales far smaller than an atom. These fluctuations did not vanish as the universe expanded. Instead, Expansion stretched them across regions large enough to influence the distribution of matter. The differences became the initial conditions for structure formation. Their origin stems from the inherent nature of quantum fields, which cannot remain completely uniform. They always contain some degree of variation. These variations were not designed. They appeared because the behavior of matter at tiny scales includes inherent randomness. Even though structure relies on randomness in its earlier stages, the development of structure depends on predictable responses to that randomness. Gravity amplifies the differences. Electromagnetic interactions stabilize matter. Cooling allows collapse. Expansion creates separation. These responses remain consistent. Randomness provides the starting points. The laws of physics shape the outcomes. Structure appears when variation meets consistency. Long-term stability also emerges because certain structures support the processes that allow them to remain intact. Stars maintain a balance between gravity and energy release. Galaxies maintain rotation that counters collapse. Planets remain in orbit because their speed matches the gravitational pull from their star. Life maintains internal structure by processing energy. These feedback loops create stability. Systems that fall outside these feedback loops eventually break apart or collapse. The presence of stable configurations allows structure to endure. The idea that structure exists because the universe supports it may seem circular at first, but this viewpoint becomes clearer when considering the range of conditions possible. A universe with different constants or different initial conditions could exist without long-lived structure. Matter might collapse into black holes immediately. Matter might disperse too rapidly. Atoms might not form. Stars might not ignite. Galaxies might not grow. The fact that the universe has parameters that allow structure indicates that these parameters fall within a range where structure can form naturally. They do not guarantee structure but permit it. Some explanations emphasize that the presence of observers influences how we perceive the universe. Observers exist only in universes that can support structure. If the universe lacked structure, observers would never develop to ask why it does. This viewpoint does not explain why the parameters have the values they do, but it explains why any beings capable of reflecting on the universe would find themselves in a universe that permits structure. It becomes a comment on observation rather than an explanation of the underlying properties. Another aspect to consider is that structure exists not because it remains perfect, but because it remains functional. Systems evolve, stars burn out, galaxies merge, planets change, life transforms. Structure is temporary on some scales but persistent on others. What remains consistent is that the rules guiding matter allow new structures to form as older ones fade. The universe continues producing new patterns because the processes that encourage structure do not end. They remain active as long as energy flows, gravity acts, and the environment contains variation. Looking at the question in this broader sense suggests that structure is not an exception in the universe. It is an outcome of how matter behaves under the conditions provided. It emerges naturally when the forces acting on matter encourage stable arrangements. It persists when these arrangements match the energy flow available. It grows when differences in density, temperature, or motion provide opportunities. These mechanisms do not require special intervention. They arise from laws that apply consistently everywhere. As these ideas come together, the picture that forms is one where structure exists because the universe's properties support it at every level. The presence of matter, the consistency of forces, the existence of variation, and the behavior of energy all contribute to a setting where structures appear and evolve. Their presence becomes a natural consequence of the starting conditions and the rules that guide everything moving forward. As the journey across the universe settles into a slower pace, it becomes easier to look back over everything that has taken place so far and notice how many different pieces have worked together to create the structures we've followed. The vast scales of galaxies, the branching shapes of the cosmic web, the steady formation of stars, and the development of life on small worlds all emerge from the same consistent rules acting in different environments. Each part adds something to the overall picture, and each reveals another angle on how the universe turns simple ingredients into long-lasting forms. Reaching this point isn't an ending, but a moment when the different threads come close enough together that the questions shift from how structures form to how they connect to the quiet fact that structure exists in the first place. When stepping back from the details, one of the first things that becomes clear is how much of the universe's behavior depends on balances rather than extremes. Stars exist because gravity and internal pressure reach a stable middle ground. Planets remain in orbit because their speed matches the pull of their parent star. Galaxies hold their shapes because the rotation of their stars aligns with the influence of dark matter. Even the cosmic web forms because gravity and expansion interact in a way that allows dense regions to develop without collapsing completely. These balances create conditions where structure can remain over long periods. They prevent systems from either tightening into singular states or dissolving entirely. They allow differences to persist long enough to grow. Looking at these balances more closely makes it easier to appreciate how structure emerges without being forced into existence. In many systems, the behaviors that create order also generate motion that seems unpredictable at smaller scales. The gas in a star-forming cloud moves chaotically, yet the cloud still collapses into new stars. The stars inside a galaxy follow orbits influenced by countless interactions, yet the galaxy maintains an overall shape. Even inside living organisms, molecules move constantly, shifting positions and exchanging energy. Yet the cells keep functioning because the processes occur within a framework capable of absorbing variation. Structure does not require absolute control. It requires environments where variation can occur without destroying the surrounding system. The universe develops these environments naturally. Expansion cools matter and separates regions without breaking them apart. Gravity brings matter together without forcing immediate collapse. Temperature shifts allow chemicals to interact in ways that support long-term stability. Over time, these influences combine to create a universe where structure appears almost everywhere matter gathers. If conditions differed significantly, structures might still form but would follow different patterns. If gravity were weaker or stronger, if particles behaved differently, or if expansion occurred at a different rate, the universe's structures would change. Even so, the underlying principle would remain the same. Structure forms where the rules allow it, guided by the behaviors of the matter present. Part of the quiet mystery surrounding these structures lies in the way they seem to create meaning simply by existing. Not meaning in an intentional sense, but meaning in the sense that they show what becomes possible when the universe follows a consistent set of rules. Stars form because gas collapses and heats. Galaxies grow because small structures merge. Planets appear in disks where collisions accumulate matter. Life emerges in settings where chemistry can operate across long time spans. Everything rests on conditions that appear simple when described individually, but become remarkable in combination. Another aspect of this mystery comes from how the universe remains dynamic, even as structure settles into stable shapes. Stars burn through their fuel, altering the chemical composition of their surroundings. Galaxies grow through mergers, changing their forms while preserving their central organization. Planetary surfaces shift through geological processes. Life adapts, changes, and responds to new challenges. None of these systems stay frozen. Their structures provide stability, but stability allows change to unfold rather than preventing it. This pattern repeats from the smallest scales to the largest. When thinking about these processes together, it becomes clear that structure is not a separate category of existence. It is one stage in the behavior of matter and energy. Matter moves, interacts, and organizes itself because the conditions allow these steps to occur. The appearance of structure does not interrupt the trend toward increasing entropy. Instead, structure becomes part of the pathway that allows entropy to rise more effectively. Stars radiate energy outward. Galaxies spread heat through collisions and gravitational interactions. Planets release energy into space. Living organisms process energy and return heat to their environment. Structure plays a role in the universe's overall progression, contributing to the system rather than resisting it. Another viewpoint emerges when considering how the universe treats variation. Variation drives structure at every level. Without small differences in density, no galaxies would have formed. Without variations in chemical composition, planets would not differ from one another. Without variations in molecular behavior, life would not evolve. Variation ensures that systems take different paths, creating a range of outcomes that persist across time. These outcomes fill the universe with complexity. They also demonstrate how sensitive structure is to initial conditions. Small differences early on become large differences later. Yet despite this sensitivity, large-scale patterns remain surprisingly consistent. This consistency suggests the universe has a natural tendency to create recognizable shapes whenever matter and energy interact over long periods. The details change, but the broad patterns repeat. Stars follow similar stages of life. Galaxies form through similar processes. Cosmic filaments stretch across space in predictable ways. Even life, though incredibly varied, relies on similar mechanisms for energy, structure, and information. These recurring patterns do not arise because the universe prefers certain shapes. They appear because the rules guiding matter lead to certain outcomes wherever the conditions match. As the picture becomes more complete, it becomes easier to recognize that structure exists not because of a single cause, but because many influences overlap. Gravity shapes the movement of matter. Electromagnetism binds particles into atoms and molecules. Temperature changes allow transitions between different states. Expansion gives systems room to develop. Quantum fluctuations introduce differences that gravity later magnifies. Dark matter reinforces the framework that guides galaxy formation. Chemical reactions support increasing complexity. Biological processes build on chemical ones. Every level depends on the level beneath it, forming a chain that stretches back to the earliest moments of the universe. Thinking about these influences together can create a sense of stillness, not because the universe is calm, but because the interactions follow steady patterns. Even though matter moves constantly, the overall behavior remains predictable at large scales. The cosmic web does not rearrange itself suddenly. Stars do not appear out of nowhere. Planets do not form instantly. Life does not emerge without long preparation. Each development requires time, consistent conditions, and the gradual accumulation of changes that support the next layer of structure. The slowness of these processes provides the stability needed for structure to persist. Questions surrounding why structure exists often lead deeper into the nature of physical laws. The values of certain constants allow atoms to remain stable. The masses of particles allow chemical reactions to occur. The strengths of the fundamental forces fall within ranges that support long-lived systems. If these values differed significantly, structure might never appear or might collapse too quickly to develop. These ideas can be examined in great detail, but the essential point remains that the universe's physical laws permit structure to arise naturally. They do not guarantee it, they allow it. Reflecting on these conditions, it becomes clear that structure is not something added to the universe. It is something that emerges whenever matter and energy evolve under the rules that govern them. When these rules lead to stable configurations, those configurations survive. When they do not, they fade. Over time, the universe becomes filled with the structures that remain. These structures form the foundation for everything else, from the largest galaxies to the smallest living organisms. Another way to consider the quiet mystery behind structure is to look at the role of time. Without immense stretches of time, many processes would not have enough opportunity to unfold. Stars require millions of years to form. Galaxies require billions. Planets take shape slowly through countless collisions. Life evolves through many generations. The universe provides the necessary time for these steps to occur. If time were limited, or if the universe changed too quickly, these developments would not take place. Time allows small influences to accumulate, guiding matter towards stable forms. This long time scale creates a sense of continuity across very different systems. The same universe that produced the first atoms eventually produced planets capable of supporting complex chemistry. The same forces that shaped galaxies also shape the environments where life can develop. This continuity does not mean the outcomes are predetermined. It means the outcomes arise from the rules and conditions present from the beginning. As these perspectives come together, the universe appears less like a place filled with isolated phenomena and more like a connected system where each level of structure builds on the next. Gas clouds gather into stars. Stars merge, scatter matter, and contribute new elements. Galaxies grow through interactions. Filaments guide matter toward clusters. Planets form in the leftovers of star formation. Life emerges in environments shaped by those planets. Each layer becomes part of the universe's larger pattern, not because it was designed to fit into a sequence, but because the rules governing matter allow such sequences to emerge. Even now, the universe continues developing. Galaxies move along the filaments of the cosmic web. Stars form in new regions while old stars fade. Planets orbit quietly, some hosting simple chemistry and others supporting deeper complexity. Life adapts, interacts, and influences its surroundings. The processes that shape structure remain active, reinforcing a pattern that stretches across the entire cosmos.